There is a galaxy so far away that its light has been traveling toward us for more than 13 billion years. It began its journey before Earth existed, before the Sun ignited, before the Milky Way settled into the spiral shape we recognize today. That light left its source when the universe was barely 300 million years old, a chaotic infant of hydrogen and helium, and it has been crossing the void ever since. It is still arriving. Photon by photon, it trickles into the mirrors of our most powerful telescopes, carrying a message from a place so distant that the very concept of distance begins to lose meaning. The galaxy is called JADESGSZ 140, and as of the latest observations from the James Webb Space Telescope, it holds the record for the most distant galaxy ever confirmed by spectroscopic measurement. Its light has been redshifted so severely that what was once ultraviolet radiation has stretched into infrared, a cosmic whisper warped by the expansion of space itself. And the distance to this object is not 13 billion light-years, it is far greater. Because space has been expanding during the entire journey of that light, the actual current distance to JADESGSZ 140 is estimated at more than 33 billion light-years away. 33 billion light-years. That number is not a typo, it is not an exaggeration. It is the calculated co-moving distance, which is the real spatial separation between us and this galaxy right now, at this very moment. And if you have ever looked up at the night sky and wondered how long it would take to travel to even the nearest star, then this number should stop you cold. Because the nearest star, Proxima Centauri, is only 4.24 light-years away. At the speed of our fastest spacecraft, it would take tens of thousands of years to reach it. The farthest confirmed galaxy is nearly 8 billion times farther than that. The arithmetic alone should be enough to make your hands feel cold. But arithmetic is not the worst part. The worst part is physics. Because the universe is not sitting still while we try to cross it. It is expanding, and it is expanding faster than we thought. And in many directions, it is expanding faster than light itself. This means that parts of the universe are already beyond our reach forever, slipping past a boundary called the cosmic event horizon, a point of no return not for objects falling into a black hole, but for entire galaxies falling out of our observable universe. So the question is not really how long it would take to reach the farthest galaxy. The question is whether it is possible at all. Whether there is any technology, any theory, any loophole in the laws of physics that could carry a human being, or even a signal, across that kind of distance, and the answer is more complicated and more disturbing than most people expect. It involves time dilation, the metric expansion of space, the energy output of entire stars, and the unsettling realization that the universe may not have been designed for exploration, not on this scale. Not ever. We like to imagine that the cosmos is a frontier, a vast open space waiting for us to venture into it. We grew up with stories of starships and warp drives and galactic empires spanning millions of worlds. But the reality is quieter, colder, and far more final than any of those stories suggest. The numbers we are going to explore tonight are not abstract. They are measurements of our confinement. They describe the walls of a prison we did not know we were in, a prison made not of stone or steel, but of expanding spacetime. A prison whose walls are moving outward at a rate that ensures no one inside can ever reach them. And the most unsettling part is this: the prison is getting smaller. Not physically smaller, but functionally smaller. The region of the universe we can interact with, the sphere of space from which we can receive signals or to which we can send them, is shrinking. Every second, more galaxies cross the cosmic event horizon and vanish from our causal reach. Every second, the universe becomes a lonelier place for any civilization living within it. By the end of tonight, you're going to understand why the farthest galaxies are not just far, but fundamentally unreachable. You will understand why the universe is structured in a way that makes cosmic isolation not a temporary problem but a permanent feature of reality. You will understand what it means to live inside a horizon, surrounded by light from places you can never visit, receiving messages you can never answer. And you will understand why the light from certain galaxies is both the first and the last message we will ever receive from them. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. The numbers ahead are vast, the distances are staggering, the implications are quiet and heavy, and they stay with you. This is a journey not across space, but into the nature of space itself, into the machinery of the cosmos and the limits it places on everything inside it, including us. We will look at what it would take to travel at light speed, at fractions of light speed, and at speeds beyond light speed. We will examine warp drives and wormholes and generation ships and uploaded minds. And we will arrive, slowly and carefully, at a conclusion that is both terrifying and strangely beautiful. A conclusion about what it means to exist in a universe that shows you everything and lets you touch almost nothing. To understand what it means to reach the farthest galaxy, we first need to understand what we mean by distance in a universe that is expanding. This is not as simple as it sounds. In everyday life, distance is fixed. The space between your house and the nearest grocery store does not change while you are driving there. You can measure it once, and it stays the same. But the universe does not work this way. The space between galaxies is growing, not because galaxies are flying apart through space like shrapnel from an explosion, but because space itself is stretching. The fabric of the cosmos is getting larger, and everything embedded in it is being carried along. This distinction matters enormously. It is the difference between objects moving through a room and the room itself getting bigger while the objects stand still. The man who first discovered this was Edwin Hubble. In 1929, working at the Mount Wilson Observatory in the San Gabriel Mountains of California, Hubble measured the light from dozens of distant galaxies and found something startling. Nearly all of them were moving away from us, and the farther away a galaxy was, the faster it was receding. This relationship, now called Hubble's law, was the first direct evidence that the universe is expanding. It was not a popular idea at the time. Even Albert Einstein had initially resisted it, inserting a term called the cosmological constant into his equations of general relativity specifically to keep the universe static. He believed, as most physicists of his era did, that the universe was eternal and unchanging. When Hubble's observations proved otherwise, Einstein reportedly called the cosmological constant his greatest blunder. But Hubble's data was clear and reproducible. The universe is not standing still. It is inflating like the surface of a balloon, and every point on that surface is moving away from every other point. Not because the points are traveling across the surface, but because the surface itself is growing. This expansion has been going on for approximately 13.8 billion years, since the event we call the Big Bang. And the rate of expansion is described by a value called the Hubble constant, which is currently measured at roughly 67 to 73 kilometers per second per megaparsec, depending on the method used. The exact value is still debated, a discrepancy known as the Hubble tension, but the approximate figure gives us what we need. A megaparsec is about 3.26 million light-years, so for every megaparsec of distance between us and a distant galaxy, that galaxy is receding from us at an additional 67 to 73 kilometers per second. At small distances, this effect is negligible. The Andromeda galaxy, our nearest large neighbor at about 2.5 million light-years, is actually moving toward us at about 110 kilometers per second because its local gravitational pull overcomes the expansion. The two galaxies are expected to collide in about 4.5 billion years. But at truly cosmic distances, the expansion dominates completely. At a distance of roughly 14 billion light-years, the recession velocity reaches the speed of light, and beyond that distance, it exceeds the speed of light. This is the crucial point that most people miss, and it is worth stating clearly. The expansion of space is not limited by the speed of light. Nothing is traveling through space faster than light. No object, no particle, no piece of information is moving through the fabric of spacetime at superluminal speed, but space itself can expand at any rate. It is not a thing within the universe obeying the universe's speed limit. It is the universe, and it sets its own rules. Right now, Galaxies beyond a certain distance are receding from us faster than 299,792 kilometers per second. Their light will never reach us. They are beyond what physicists call the cosmic event horizon. They are falling away into an inaccessible region of the universe, a region that grows larger every second. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, has a radius of about 46.5 billion light-years. This number is confusing at first glance. If the universe is only 13.8 billion years old, how can we see objects 46.5 billion light-years away? The answer, again, is expansion. When that light was emitted, the objects were much closer, but space has been stretching during the entire 13.8 billion years that the light was in transit, carrying the source farther and farther away. By the time the light arrives at our telescopes, the object that emitted it has been carried to a co-moving distance of 46.5 billion light-years. So the observable universe is not a sphere 13.8 billion light-years in radius. It is a sphere 46.5 billion light-years in radius, with a total diameter of about 93 billion light-years. But the actual universe, the totality of everything that exists, may be vastly larger than this observable portion. Some estimates from inflationary cosmology suggest the full universe could be at least 250 times wider than what we can see. Other models suggest it could be infinite, stretching forever in all directions with no edge, no boundary, and no center. We simply do not know. The observable universe is our window, and it shows us only a fraction of what might be out there. It is like standing on the shore of an ocean and being able to see only to the horizon. The ocean extends far beyond what your eyes can reach, but you have no way of knowing how far. Let us try to make these numbers feel real, because the human mind is not equipped to process distances measured in billions of light-years. Our brains evolved to navigate savannas and forests. To judge the distance to a tree or a predator, we can intuitively grasp a few kilometers. With effort, we can imagine the distance between cities or across countries, but cosmic distances overwhelm our perceptual systems entirely. They are not just big, they are incomprehensibly big. So we need comparisons. Imagine shrinking the entire observable universe down to the size of Earth. In this model, our planet, real Earth, becomes a sphere roughly 12,742 kilometers in diameter, the same as it actually is. Now, in this shrunken cosmos, the Milky Way galaxy, which in reality is about 100,000 light-years across, would be roughly 0.014 millimeters wide. That is about 1/7 the width of a human hair. You could not see it without a powerful microscope. It would be a speck so small that it would be invisible to the naked eye. The distance to the Andromeda galaxy, our nearest large neighbor, at 2.5 million light-years, would be about 0.035 millimeters. Two invisible specks, separated by a gap smaller than the thickness of a sheet of paper. This is the local universe, the immediate neighborhood that we consider close. Now, in this same model, the distance to JADES GSZ140, the farthest confirmed galaxy, would stretch to about 4,500 kilometers. That is roughly the distance from London to Baghdad, or from New York to Los Angeles and then halfway back again. If the entire observable universe were the size of Earth, our galaxy would be an invisible speck. The nearest neighboring galaxy would be another invisible speck right next to it. And the farthest galaxy we have ever detected would be thousands of kilometers away from those specks. The emptiness between them is almost everything. The matter, the stars, the galaxies, they are rounding errors in a vast ledger of nothing. Here is another way to feel the distance. Light travels at approximately 299,792 kilometers per second. That is fast enough to circle the equator of the Earth 7.5 times in a single second. A beam of light can reach the moon in about 1.3 seconds. It reaches the sun in about 8 minutes and 20 seconds. It crosses the entire solar system, from the sun to the orbit of Neptune, in about 4 hours and 10 minutes. It travels from the sun to the outer edge of the Oort cloud, the shell of icy objects that marks the Sun's gravitational boundary in roughly 1 to 2 years. But to cross the Milky Way, that same beam of light needs 100,000 years. To reach the Andromeda galaxy, it needs 2.5 million years. And to reach JADES GSZ140 at its current co-moving distance of approximately 33 billion light-years, light would need 33 billion years. And now, except it cannot get there in 33 billion years, because the space between here and there is expanding faster than light can cross it. The galaxy is already beyond the cosmic event horizon. It is already lost to us. The light we see from it is ancient light, emitted when the galaxy was much closer, in a much smaller, much younger universe. Now consider human spacecraft, because this is where the numbers become truly sobering. The fastest object ever launched from Earth by human engineering is the Parker Solar Probe, a NASA mission launched in August 2018 to study the Sun's outer corona. During its close approaches to the Sun, the probe uses the Sun's gravity to accelerate to extraordinary speeds, reaching approximately 635,000 kilometers per hour during its closest perihelion passages. That sounds impressive. It is impressive by any earthly standard. It is fast enough to fly from New York to Tokyo in about 14 seconds. But compared to the speed of light, it is moving at roughly 0.059% of light speed, less than 1/16th of 1%. At this speed, reaching even the nearest star, Proxima Centauri, at 4.24 light-years would take about 6,800 years. That is longer than all of recorded human history. Reaching the center of our own galaxy, roughly 26,000 light-years away, would take about 42 million years. Reaching the Andromeda galaxy would take about 4 billion years. And reaching JADES GSZ140 at its current co-moving distance would take approximately 56 trillion years. That is more than 4,000 times the current age of the universe. If you had launched the Parker Solar Probe at the very instant of the Big Bang, it would have covered less than 1/4000th of the distance to the farthest galaxy by now. If the Sun were the size of a basketball, about 24 centimeters in diameter, then Earth would be a small peppercorn roughly 26 meters away. Jupiter would be about the size of a large marble, 135 meters from the basketball. The nearest star, Proxima Centauri, would be another basketball approximately 6,900 kilometers away, about the distance from New York City to Tokyo. In this model, the entire Milky Way galaxy would span roughly 160 million kilometers, larger than the real distance from Earth to the Sunday, and the farthest confirmed galaxy. In this basketball sun model, JADESGSZ140 would be so far away that the distance becomes impossible to state in meaningful terms. It would be approximately 5.6 billion kilometers from the basketball in your hands. That number is so large that it exceeds the number of grains of sand on all the beaches of Earth. There is no analogy on this planet large enough to contain it. It spills out of every comparison we try to make, defeating our attempts to grasp it as surely as the expansion of space defeats our attempts to cross it. Let us try one more comparison, because it is the one that haunts me the most. Imagine that you could drive a car to the farthest galaxy. A normal car on a normal road at highway speed, about 100 kilometers per hour. At that speed, you would reach the moon in about 160 days. You would reach the sun in about 171 years. You would reach the nearest star, Proxima Centauri, in about 46 million years, and you would reach JADESGSZ140 at its current co-moving distance in about 356 quadrillion years. That is 356, followed by 15 zeros. The universe itself will have long since died a heat death before you arrive. The stars will have burned out. The black holes will have evaporated. The last particles will have decayed. And your car will still be driving through a universe of absolute darkness and absolute cold toward a destination that no longer exists, along a road that is stretching faster than your wheels can turn. The scientists who study these distances use a variety of extraordinary tools. The most important in recent years has been the James Webb Space Telescope, or JWST, launched on the 25th of December 2021, aboard an Ariane 5 rocket from the European Space Agency's launch site in Kourou, French Guiana. The telescope was positioned at the second Lagrange point, or L2, a gravitationally stable location approximately 1.5 million kilometers from Earth, on the side opposite the Sunday. From this vantage point, shielded from the sun and Earth's heat by a tennis court-sized sunshield, the telescope's 6.5-meter primary mirror collects infrared light with unprecedented sensitivity. Its mirror is made of 18 hexagonal segments coated in a thin layer of gold, each segment precisely aligned to function as a single parabolic surface. The gold coating is essential because gold is highly reflective in the infrared, the wavelength range where the most distant galaxies emit their light after billions of years of redshifting. It was the James Webb Space Telescope that confirmed the distance to Jade's GS Z140 inches early 2024, using a technique called spectroscopic redshift measurement. By capturing the spectrum of the galaxy's light and identifying specific emission lines, hydrogen lines and possibly oxygen lines that are produced at known wavelengths, astronomers could measure how far those lines had been shifted toward longer wavelengths by the expansion of space. The redshift value, denoted as Z, was measured at approximately 14.32. This means that the wavelengths of the light are now 15.32 times longer than when they were emitted, stretched by a factor of 1 plus Z. At this redshift, the galaxy was emitting light predominantly in the ultraviolet range, but by the time that light reaches us, it has been stretched well into the infrared, far beyond the range of human vision. Using the standard lambda CDM cosmological model with parameters derived from the Planck satellite's measurements of the cosmic microwave background, astronomers calculated that this redshift corresponds to a look-back time of approximately 13.5 billion years and a co-moving distance of more than 33 billion light-years. Before JWST, the observational frontier was held by the Hubble Space Telescope, which orbited Earth from April 1990 until its decommissioning. Hubble's 2.4-meter primary mirror collected visible and near-infrared light, allowing it to push the record for the most distant galaxy several times over its operational lifetime. The Hubble Deep Field images, first captured in December 1995 under the direction of Space Telescope Science Institute Director Robert Williams, revealed thousands of galaxies in a patch of sky no larger than a grain of sand held at arm's length. That patch was deliberately chosen to be empty, a region where no bright stars or known structures interfered. And when Hubble stared at that tiny blank square of sky for 10 consecutive days, it found galaxies, thousands of them, faint, ancient, distant galaxies stretching back billions of years. That image changed our understanding of the cosmos in a fundamental way. It showed that galaxies are not rare. They are everywhere, in every direction, at every distance, filling the observable universe with a density that defies casual imagination. Current estimates suggest that the observable universe contains approximately 2 trillion galaxies, each containing anywhere from a few billion to several hundred billion stars. The total number of stars in the observable universe is estimated at roughly 200 sextillion, or 2 times 10 to the power of 23. To put that in perspective, it is more stars than grains of sand on every beach and in every desert on Earth. It is a number so large that if you counted 1 star per second, without sleeping, without pausing, it would take you more than 6 quadrillion years to count them all. The universe is not empty. It is teeming with matter and energy and structure, but it is also overwhelmingly vast, and the distances between the structures are staggering. Despite all this matter, the universe is almost entirely empty space. The average density of the observable universe is about 5.9 protons per cubic meter. That is roughly 6 hydrogen atoms in a volume the size of a large closet. It is a near-perfect vacuum, emptier than anything we can create in a laboratory on Earth. If you could somehow fly through space in a straight line at near light speed, you would travel for millions of light years between galaxies, passing through nothing but dark, cold, silent space sprinkled with a few stray hydrogen atoms per cubic meter. The occasional photon from the cosmic microwave background would pass through you, a relic of the Big Bang cooled to 2.7 degrees above absolute zero. But aside from that, there would be nothing. No light. No sound. No matter worth mentioning. Just the void, stretching in every direction. For millions of light years at a time, the universe is not a crowded room. It is a vast, silent desert with occasional oases of light, separated by incomprehensible stretches of nothingness. This is the landscape we must cross if we want to reach the farthest galaxy. A desert that is growing larger every moment, whose expansion is accelerating, whose emptiness is increasing, and whose horizons are receding faster than the fastest thing in the universe can chase them. And we have not yet talked about what happens when you actually try to cross it. We have not talked about the energy required, the time involved, the physics that bends and breaks at these scales. We have not talked about what happens to a traveler who sets out toward a destination that is running away from them faster than they can ever hope to move. We have not discussed time dilation, the bizarre slowing of clocks at high speeds. We have not discussed the Alcubierre metric, the closest thing physics has to a theoretical warp drive. We have not discussed wormholes, generation ships, or the thermodynamic limits of propulsion. To understand the magnitude of the problem, it helps to compare the journey to familiar timescales. The oldest known fossils on Earth, evidence of microbial life preserved in ancient rocks in Western Australia, are roughly 3.5 billion years old. Life has existed on this planet for about a quarter of the age of the universe. Complex multicellular life has existed for only about 600 million years. The dinosaurs appeared about 230 million years ago and went extinct 66 million years ago. Modern humans, Homo sapiens, have existed for roughly 300,000 years. Recorded human history spans about 5,000 years. The entire industrial era, from the invention of the steam engine to the launch of the James Webb Space Telescope, covers barely 250 years. That is the blink of an eye on the cosmic timescale. If the age of the universe were compressed into a single calendar year, with the Big Bang occurring at midnight on January 1, then the Sun and Earth would form around September 2. The first simple life on Earth would appear around September 21. Dinosaurs would appear on December 25 and go extinct on December 30. The entire history of Homo sapiens would fit into the last 13 minutes of December 31. Recorded civilization would occupy the final 10 seconds, and the age of space exploration, from Sputnik to today, would be less than 1/10 of a second. Now set that blink of an eye against the timescale of a journey to the farthest galaxy. Even at the speed of light, the journey would take 33 billion years. That is more than twice the current age of the universe. It is more than 9 times the age of the Earth. It is a number so large that the entire history of life on our planet could repeat itself many times over before the journey was complete. And at the speed of our fastest spacecraft, the journey would take more than 50 trillion years, a span of time that dwarfs even the projected lifetime of the stars. The last red dwarf stars, the smallest and most fuel-efficient stellar objects, will burn for roughly 10 to 15 trillion years before exhausting their hydrogen fuel. So a spacecraft launched today toward the farthest galaxy would still be in transit long after the last star in the universe has gone dark. There is a lesson in these numbers. The universe is not just vast in space, it is vast in time, and the two kinds of vastness conspire against us. To cross great distances, you need great speed. To achieve great speed, you need great energy, and even with the greatest conceivable speed, you need enormous amounts of time. The speed of light is the ceiling, and even that ceiling is not high enough to bridge the gaps between distant galaxies, because those gaps are growing while you try to cross them. Time and space and expansion form a triple lock on the cosmos, and no single key opens all three. It is worth pausing to note that these distances were not always known. For most of human history, the universe was thought to be small. The ancient Greeks placed the stars on a crystalline sphere a modest distance beyond Saturn. In the medieval European world, the cosmos was a nested set of heavenly spheres, compact and orderly, with Earth at the center. Even after Copernicus displaced Earth from the center of the solar system in 1543, the size of the universe was still wildly underestimated. It was not until 1838 that the German astronomer Friedrich Bessel made the first successful measurement of stellar parallax, the tiny apparent shift in a star's position as the Earth moves around the Sunday. Bessel measured the parallax of the star 61 Cygni and determined it was about 10.3 light-years away. This was the first direct evidence that the stars were enormously distant, far beyond the scale of the solar system. The true scale of the universe only emerged in the 20th century. In the 1920s, Edwin Hubble, using the 100-inch Hooker telescope at Mount Wilson, demonstrated that the so-called spiral nebulae were not clouds of gas within the Milky Way but entire galaxies far beyond its borders. The Andromeda Nebula, as it was then called, was revealed to be the Andromeda Galaxy, a collection of hundreds of billions of stars, roughly 2.5 million light-years from Earth. This discovery shattered the last remnant of the small universe. Overnight, the cosmos expanded from a single galaxy to a vast archipelago of galaxies scattered across millions of light-years, and as telescopes grew more powerful, the distances grew larger. The Sloan Digital Sky Survey, which began operations in the year 2000, mapped over 1 million galaxies and revealed the large-scale structure of the cosmos, showing that galaxies are organized into filaments, walls, and clusters separated by enormous voids. The largest known structures in the universe, galactic superclusters like the Laniakea supercluster, of which the Milky Way is a part, span hundreds of millions of light-years. And yet even these structures are small compared to the full extent of the observable universe. Laniakea is about 500 million light-years across. The observable universe is about 93 billion light-years across. Laniakea is a neighborhood. The observable universe is a continent. And the full universe, whatever it is, may be an ocean so large that the entire observable universe is lost within it like a single drop of water. We are small. We are brief. We are here. And from here, the farthest galaxy is so distant that every method of measuring it strains the limits of our mathematics and our imagination. The light from JADES GSZ 140 has crossed more than 97% of the observable universe to reach us. It carries information from a time when the cosmos was a fraction of its current size, a fraction of its current age, and a fraction of its current emptiness. It is a fossil of light, ancient beyond reckoning, and it tells us something profound about the barrier we face. To make the scale of the challenge concrete, consider one final thought experiment. Imagine laying out a ruler from Earth to J, A, D, E, S, G, S, Z, 1, 4, 0. Not a physical ruler, of course, but a conceptual one, a straight line through space marking the co-moving distance of 33 billion light-years. Now imagine dividing that ruler into segments, each one equal to the distance from Earth to the Sun, about 150 million kilometers, a distance astronomers call 1 astronomical unit. How many segments would you need? The answer is approximately 2.08 quadrillion. That is, 2.08 times 10 to the power of 15. If you laid down 1 segment per second, it would take you 66 million years to finish laying the ruler, and that is just the measuring. The travelling would be incomparably longer, or think of it in terms of the cosmic microwave background, the oldest light in the universe. This radiation was emitted roughly 380,000 years after the Big Bang, when the cosmos cooled enough for atoms to form and for light to travel freely for the first time. That light has been travelling for 13.8 billion years and now forms a faint glow that fills all of space, detectable in every direction. The surface from which this light was emitted, known as the surface of last scattering, is now approximately 46 billion light-years away due to expansion. JADES GSZ140, at 33 billion light-years, is closer to us than the surface of last scattering. But the light from the galaxy is nearly as old as the cosmic microwave background itself. The galaxy existed in an era only slightly younger than the moment the universe became transparent to light. We are seeing it at the edge of accessibility, at the boundary of what the universe allows us to witness. And there is a profound irony embedded in all of this. The reason we can see JADES GSZ140 at all is precisely because we cannot reach it. Its light was emitted billions of years ago, when the universe was small enough for photons to bridge the distance. That same expansion that carried the galaxy beyond our reach is what stretched its light to wavelengths our infrared telescopes can detect. Without expansion, the light would still be ultraviolet, invisible to the James Webb Space Telescope. Without expansion, the galaxy would still be close enough to visit. The same process that shows us the galaxy is the process that takes it away. We see it because we lost it. The universe offers us its portrait as consolation for its departure. This is the central tension of cosmology. We live in a universe that reveals itself in exquisite detail, allowing us to trace its history back to within a fraction of a second after its birth, while simultaneously making the vast majority of itself permanently inaccessible. It is a universe that shows and hides, that illuminates and obscures, that whispers its secrets across billions of years of light travel time, and then retreats behind the advancing curtain of expansion. The observable universe is a window that is slowly closing. Every galaxy we can see today is a star in a show that will not run forever. And the farthest galaxy, JADES GSZ140, is the most distant seat in the theatre, the view from the very last row, where the actors are almost too faint to see and the curtain is already descending. That is where the real trouble begins, and the trouble is deeper, stranger, and more permanent than you might expect. Because everything we have discussed so far, the expansion of space, the recession of galaxies, the unimaginable distances, these are just the context. They are the landscape. The real question is what happens when you try to move through that landscape. What happens when physics meets ambition, when engineering meets the speed of light, when human ingenuity encounters the expansion of the cosmos? The answer is not encouraging. But it is worth understanding fully, because in understanding it, we come to know the shape of our confinement, and knowing the shape of your prison is the first step toward understanding your place within it. The core problem is deceptively simple to state. The farthest galaxy is moving away from us faster than the speed of light, and nothing with mass can travel at or above the speed of light. These two facts, taken together, seem to close the door permanently. But the full picture is more nuanced, more layered, and ultimately more unsettling than a simple statement of impossibility. To understand why the farthest galaxy is beyond reach, we need to understand both halves of the equation: the speed limit imposed by physics and the expansion rate imposed by cosmology. And we need to understand how they interact, because it is the interaction that creates the trap. Let us start with the speed of light, because this is where most misunderstandings begin. The speed of light in a vacuum, approximately 299,792 kilometers per second, is not just a speed limit in the way that a highway speed limit is a speed limit. A highway speed limit is arbitrary. It is set by humans and enforced by humans. You can break it if you choose to accept the consequences, but the speed of light is not like this. It is a structural feature of space-time itself. It is woven into the geometry of the universe at the most fundamental level. Albert Einstein established this in 1905 with his special theory of relativity, building on earlier work by Hendrik Lorentz and Henri Poincaré. The theory has been confirmed by every experiment conducted since, including particle accelerator experiments at CERN, precision measurements of satellite clocks, and observations of high-energy cosmic rays. The reason nothing with mass can reach the speed of light is rooted in the relationship between energy and mass. As an object accelerates, its kinetic energy increases. But in special relativity, energy and mass are related by the famous equation E equals mc squared. As an object approaches the speed of light, its relativistic mass, the effective resistance to further acceleration, increases without bound. The energy required to push it faster grows exponentially. At 90% of the speed of light, an object has about 2.3 times its rest mass energy. At 99%, about 7.1 times. At 99.9%, about 22.4 times. At 99.99%, about 70.7 times. At 99.9999%, about 707 times. The pattern is clear. As the velocity approaches c, the energy required approaches infinity. You can pour in more and more energy and get closer and closer to light speed, but you never reach it. The speed of light is a wall that gets thicker the harder you push against it. To make this concrete, consider the Large Hadron Collider at CERN, near Geneva, Switzerland. This 27-kilometer ring accelerates protons to 99.999999, 1% of the speed of light. Each proton, with a rest mass of just 1.67 times 10 to the power of negative 27 kilograms, requires an energy of about 6.5 tera-electron-volts. The collider consumes roughly 200 megawatts of electrical power to maintain these beams, and yet, despite all this energy, the protons are still not traveling at the speed of light. They are unimaginably close, but not there. The remaining 0.0000009% gap, tiny as it seems, would require infinite energy to close. This is not a limitation of technology. It is a law of nature. It applies equally to rockets, ion drives, antimatter engines, photon drives, and any propulsion system that operates within the framework of Einstein's relativity. The universe has a speed limit, and it enforces it with the full weight of mass-energy equivalence. Now let us turn to the other half of the problem, the expansion of the universe. We have already discussed the Hubble constant and the fact that distant galaxies are receding from us due to the expansion of space. But we need to go deeper, because the expansion is not constant. It is accelerating, and this acceleration changes everything. The discovery of the accelerating expansion is one of the most important findings in the history of cosmology. It was made in 1998 by two independent teams of astronomers. The Supernova Cosmology Project, based at Lawrence Berkeley National Laboratory and led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt at the Australian National University and Adam Rees at Johns Hopkins University. All three men would share the Nobel Prize in Physics in 2011 for this discovery. The teams were studying Type Ia supernovae, a specific class of stellar explosion that occurs when a white dwarf star in a binary system accumulates enough matter from its companion to trigger a thermonuclear detonation. Type Ia supernovae are valuable to cosmologists because they all explode with roughly the same intrinsic brightness, making them standard candles, objects whose true luminosity is known. By comparing the observed brightness of a Type Ia supernova with its known intrinsic brightness, astronomers can calculate its distance, and by measuring the redshift of the supernova's host galaxy, they can determine how fast it is receding. Plot distance against recession speed, and you get a curve that describes the expansion history of the universe. What both teams found was that the distant supernovae were dimmer than expected. They were farther away than the existing models predicted. The only explanation was that the expansion of the universe was not slowing down, as gravity should cause it to do, but speeding up. Something was counteracting gravity on the largest scales, pushing galaxies apart with increasing force. That something was eventually named dark energy, and it remains one of the most profound mysteries in all of physics. Dark energy makes up approximately 68% of the total energy content of the universe. Ordinary matter, the stuff of stars and planets and people, makes up only about 5%. Dark matter, a different mysterious substance that exerts gravitational attraction but does not emit or absorb light, accounts for about 27%. Together, dark matter and dark energy constitute 95% of everything there is. And we understand neither of them. At a fundamental level, we know what they do, we can measure their effects, but we do not know what they are. Dark energy, in particular, behaves like a property of empty space itself, a tiny but relentless energy that permeates every cubic centimeter of the vacuum and drives the expansion of the cosmos at an ever-increasing rate. The implications of accelerating expansion are staggering. In a universe with constant expansion, distant galaxies would recede at a fixed rate, and there would be a fixed cosmic event horizon. We could, in principle, catalogue all the galaxies we will ever be able to see. But in a universe with accelerating expansion, the situation is grimmer. The event horizon is not fixed. It is shrinking in co-moving coordinates. Galaxies that are currently just inside the horizon will eventually cross it and become permanently invisible. The pool of galaxies we can communicate with, even in the most optimistic theoretical scenario, is getting smaller with every passing year. To put a number on it, the current co-moving distance to the cosmic event horizon is approximately 16.5 billion light-years. Any light emitted from a galaxy within this radius right now will eventually reach us, given enough time, but any light emitted from beyond this radius will never arrive. The expansion will carry it backward, stretching its wavelength toward infinity, dissipating its energy into the void. JADESGSZ140, at a co-moving distance of more than 33 billion light-years, is roughly twice the distance to the event horizon. It is hopelessly beyond the boundary, and the boundary is moving closer. In a few 100 billion years, it will have receded to include only the galaxies of our own local group, the Milky Way, Andromeda, and a few dozen smaller companions bound to us by gravity. Everything else will be gone. So now let us try to answer the central question directly. How long would it take to reach the farthest galaxy? Let us approach this methodically, considering several speeds and the effects of expansion at each one. First, the speed of light. If we could somehow build a spacecraft capable of traveling at exactly the speed of light, ignoring for now the physical impossibility of accelerating a massive object to that speed, how long would the journey take? The naive answer would be 33 billion years, since the galaxy is 33 billion light-years away. But this answer is fundamentally wrong. It fails to account for the expansion of space during the journey. The galaxy is not standing still. It is receding, carried by the expansion at a velocity that, at its current distance, far exceeds the speed of light. A light-speed ship aimed at the galaxy's current position would arrive at that point after 33 billion years, only to find that the galaxy has moved much farther away during the trip. The ship would need to continue onward, but the galaxy would still be receding. The ship would be like a swimmer in a river, swimming toward a point on the opposite bank, only to find that the river is getting wider, faster than the swimmer can cross it. The swimmer never reaches the other side. The gap increases. The swimmer tires, the river wins. In technical terms, the galaxy is beyond the event horizon. No signal and no ship, even one traveling at light speed, can ever reach it from our position. The expansion of the intervening space will always outpace the forward motion of the ship. This is not a matter of waiting long enough. It is a permanent impossibility. What about sublight speeds? At 50% of the speed of light, the situation is even worse. The ship would be slower than light, and the galaxy is receding faster than light. The gap would widen from the moment of departure and continue widening forever. At 90% of light speed, the same. At 99%, the same. At 99.9999%, still the same. The recession velocity of JADESGSZ140 at its current co-moving distance is approximately 2.2 times the speed of light. No sublight ship can close a gap that is opening at twice the speed of light. But here is where the physics gets truly strange. Einstein's special theory of relativity introduces a phenomenon called time dilation. When an object moves at a significant fraction of the speed of light relative to an observer, time passes more slowly for the moving object than for the stationary observer. This effect is not hypothetical. It has been measured directly using atomic clocks on aircraft and satellites, and it is routinely accounted for in the operation of GPS systems, which would drift by several kilometers per day without relativistic corrections. The faster you travel, the slower your clock ticks relative to the clocks of those you left behind. At 99% of the speed of light, time for the traveler passes about 7.1 times slower than for someone on Earth. At 99.99%, about 70.7 times slower. At 99.9999%, about 707 times slower. At 99.9999999%, time passes about 70,711 times slower. This means that a journey of enormous duration, as measured by clocks on Earth, could feel much shorter to the person aboard the ship. In theory, if you could sustain constant acceleration at 1g, the comfortable pull of Earth's gravity, you could reach extremely distant objects in a surprisingly short subjective time. After 1 year of acceleration at 1g, you would be traveling at about 77% of the speed of light. After 2 years, about 97%. After 5 years, 99.99%. After 10 years of subjective time, you would have crossed thousands of light years as measured from Earth. After 20 years, millions. After 30 years, billions. The mathematics of relativistic acceleration is beautiful in this way. It compresses vast cosmic distances into manageable human lifetimes, at least from the traveler's frame of reference. This might seem like a solution. If time dilation can compress a billion-year journey into a few decades of subjective experience, then perhaps reaching the farthest galaxy is possible after all, at least for the traveler. But the hope is an illusion. Time dilation helps the traveler's subjective experience. It does nothing for the universe. While the traveler ages 20 years, billions of years pass in the rest of the cosmos. Stars are born and die. Civilizations rise and fall. The universe ages and cools and expands. And crucially, the destination does not experience time dilation. It continues to recede. It continues to be carried by the expansion of space. The expansion does not care about the traveler's reference frame. It operates on cosmic time, the time measured by the universe as a whole. So even with extreme time dilation, the physical distance between the traveler and the galaxy is still increasing faster than the traveler can reduce it. The traveler might feel like the journey is short. But the journey is not short, it is infinite. And feeling otherwise does not change the physics. There is also the brutal matter of energy. The energy required for relativistic travel is not merely large, it is astronomical in the most literal sense of the word. Let us work through some numbers. To accelerate a spacecraft with a rest mass of 1,000 kilograms, roughly the mass of a small car, to 99% of the speed of light requires approximately 5.7 times 10 to the power of 19 joules. To put that in context, it is roughly the total energy output of the Sun in 1.5 seconds for a single small vehicle. To reach 99.99%, the energy requirement jumps to about 4.5 times 10 to the power of 21 joules, equivalent to several hours of the Sun's total output. And to reach 99.9999%, we are talking about the Sun's total output over multiple days, all concentrated into accelerating a single object. And it gets worse. These calculations assume perfect efficiency, with no wasted energy. In reality, any propulsion system will waste some energy as heat or exhaust. They also assume you only need to accelerate. If you want to arrive at your destination rather than zip past it, you need to decelerate as well, which roughly doubles the energy requirement. And if you want to come back, double it again. A round trip to a distant star at relativistic speeds would require energy on the scale of stellar output, focused into a single vehicle, with engineering precision that is currently beyond any known or proposed technology. For constant acceleration at 1g, sustained over decades of subjective time, the energy budget enters the truly absurd. After 30 years of ship time, the spacecraft would have consumed more energy than some stars produce in their entire lifetimes, and this is for a tiny ship. For a vessel capable of carrying human passengers in life support conditions, with all the associated mass of food, water, air, radiation shielding, and structural materials, the numbers would be many orders of magnitude larger. In 1960, The physicist Robert Bussard proposed a concept called the ramjet, which he envisioned as a solution to the fuel problem. The idea was elegant. Instead of carrying all your fuel with you, you scoop up hydrogen from the interstellar medium as you fly, compress it, and use it as fuel for a fusion reactor. Since interstellar space contains a thin but ubiquitous sea of hydrogen atoms, roughly 1 atom per cubic centimeter on average, a sufficiently large scoop could collect enough fuel to sustain continuous acceleration indefinitely. The Bussard ramjet promised unlimited range, because the fuel would always be ahead of you, waiting to be gathered. But subsequent analysis revealed severe problems. The hydrogen scoop would need to be enormous, perhaps hundreds of kilometers in diameter, to collect enough atoms at such low densities. The drag from scooping up this hydrogen, essentially running into trillions of particles per second, would create resistance that at high speeds would exceed the thrust generated by fusing the collected hydrogen. The ramjet would accelerate at low speeds, but hit a maximum velocity beyond which the drag overpowered the thrust. Various modifications have been proposed, including using the scoop only to collect fuel while the thrust comes from an onboard reactor, but none have solved the fundamental drag problem. The Bussard ramjet, like the Alcubierre drive and the traversable wormhole, remains a tantalizing idea that collapses under the weight of physical reality. And then there is the problem of the interstellar medium itself. Space is not perfectly empty. Between the stars, there exist thin clouds of gas and dust, regions of ionized plasma, and high-energy particles called cosmic rays. At relativistic speeds, even a thin gas becomes a lethal hazard. A hydrogen atom that is harmless at rest becomes a tiny bullet at 99% of the speed of light. The kinetic energy of each atom, relative to the ship, is enormous. At 99.9% of light speed, a single proton carries as much energy as a fast-moving baseball. Now multiply that by the billions of atoms the ship would encounter per second. The result is a continuous bombardment equivalent to intense nuclear radiation. The ship's hull would need shielding thick enough to absorb this radiation, which adds mass, which increases the energy required to accelerate, which makes the problem worse. It is a vicious cycle with no clean solution. So here is where we stand. The farthest galaxy is 33 billion light-years away. It is receding faster than the speed of light. Nothing with mass can reach or exceed the speed of light. Time dilation helps the traveler's subjective experience but does not change the physical distance or the expansion rate. The energy required for near light-speed travel is equivalent to the output of stars, far beyond any known or foreseeable technology. The interstellar medium makes relativistic travel physically dangerous, even if the energy is available, and the expansion of space is accelerating, meaning the problem is getting worse with every passing moment. Every second, the farthest galaxy moves a little farther away. Every second, the cosmic event horizon draws a little closer. Every second, the window of possibility closes by a tiny fraction, and there is nothing we can do to stop it. The mathematics of cosmology describes this situation with cold precision. The scale factor of the universe, denoted by the letter A, increases over time according to the Friedmann equations, a set of differential equations derived from Einstein's general relativity. In a universe dominated by dark energy with a cosmological constant, the scale factor grows exponentially. This means the distances between galaxies do not just increase linearly, they increase faster and faster, compounding like interest in a savings account. But instead of money growing, it is emptiness growing. And the rate of compounding is set by dark energy, which appears to be constant, unwavering, and relentless. There is no mechanism in known physics to stop it, slow it, or reverse it. Every probe we could send, every signal we could broadcast, every photon we could aim at the farthest galaxy would share the same fate. It would travel at the speed of light or slower, and it would fall behind the expanding space, never closing the gap, eventually losing its energy to redshift, fading into the cosmic background, and vanishing. We would send a message into the void, and the void would swallow it. But here's what makes this truly terrifying. The problem is not just that the farthest galaxy is unreachable. The problem is that the unreachability is spreading. The cosmic event horizon is not a static boundary. It is a dynamic one, and it is advancing inward. Galaxies that are currently within our event horizon will, over time, cross it and become permanently invisible. The pool of reachable galaxies is shrinking. The observable universe, in a practical sense, is dying, not with a bang, not with a collapse, but with a slow, silent, irreversible retreat of everything we can see. Consider what this means in detail. Right now, there are approximately 2 trillion galaxies in the observable universe. Many of these, the ones beyond the event horizon at 16.5 billion light-years co-moving distance, are already unreachable by any signal we send today. But we can still see them because their light was emitted long ago, when they were closer. We see them as they were, not as they are. And the number of galaxies whose light can still reach us is getting smaller with every passing year. The astronomer Abraham Loeb at Harvard University has calculated the timeline of cosmic isolation in sobering detail. Within the next 100 billion years or so, every galaxy outside the local group, our gravitationally bound cluster of about 54 galaxies dominated by the Milky Way and Andromeda, will have crossed the event horizon. The local group will remain together because its internal gravity is strong enough to resist the cosmic expansion. The Milky Way and Andromeda will have merged into a single large elliptical galaxy, sometimes speculatively called Milkomeda or Milkdromeda, and that merged galaxy, along with a few small satellite galaxies, will be the only visible structure in the entire sky. Imagine being an astronomer in that era. You point your telescope at the sky and you see your own stars. You see nothing else, no other galaxies, no evidence that anything exists beyond your own stellar system. The cosmic microwave background radiation, which today provides our strongest evidence for the Big Bang, will have been redshifted to wavelengths so long that it will be undetectable by any conceivable instrument. The temperature of this radiation, currently 2.725 Kelvin, will have dropped to effectively zero. There will be no fossil light to study, no distant supernovae to observe, no galaxy surveys to conduct. Cosmology, as a science, will be impossible. The evidence will have been erased by the very expansion that created it. This is not speculation. This is the straightforward prediction of the Lambda CDM model, the standard model of cosmology, which is based on the best available data from the Planck satellite, the Sloan Digital Sky Survey, the Dark Energy Survey, and dozens of other observational programs. The model has been tested against multiple independent lines of evidence and has passed every test. The accelerating expansion of the universe is as well established as any fact in modern physics, and its long-term consequence is the erasure of cosmic history. Let us now consider the problem from a different angle, one that reveals even more about the nature of our confinement. Suppose we ignore the farthest galaxy for a moment and ask a simpler question. What is the most distant galaxy we could theoretically reach if we left right now, traveling at the speed of light? The answer is not intuitive. You might think that a light-speed traveler could reach any galaxy currently within the observable universe, given enough time. But this is wrong. The observable universe extends 46.5 billion light-years in radius, but the event horizon is only about 16.5 billion light-years in co-moving distance. The event horizon tells us the boundary within which light emitted today could still reach a destination before the expansion carries that destination out of range. So a photon leaving Earth right now could, in principle, reach any galaxy currently within 16.5 billion light-years, although it would take an extremely long time to do so. But any galaxy currently beyond 16.5 billion light-years is beyond the reach even of light. This means that of the 2 trillion galaxies in the observable universe, only a fraction are within our causal reach. The exact fraction depends on how the galaxies are distributed in co-moving distance, but rough estimates suggest that only about 3 to 5% of currently observable galaxies are within the event horizon. The other 95 to 97% are already beyond our reach. We can see them, we can photograph them, we can study their light. But we can never send them a signal, never visit them, never influence them or be influenced by them again. They are exhibits in a museum, beautiful, distant, and behind glass that will never be opened. And the situation gets worse with each passing year. As the expansion accelerates, the event horizon shrinks in co-moving coordinates. Galaxies that are currently just inside the boundary will eventually drift outside it. A galaxy that is 16 billion light-years away today might be reachable if we sent a light signal right now, but if we wait 1 billion years, the expansion during that delay will have pushed the galaxy past the threshold. Hesitation has a cost. Every year we do not act, the range of the possible contracts. The universe is not patient. It is not waiting for us to develop the technology to explore it. It is retreating, and it will not stop. There is a concept in physics called the affectable universe, distinct from the observable universe. The observable universe is the set of events whose past light cones intersect our current position, meaning their light has had time to reach us. The affectable universe is the set of events whose future light cones intersect our current position, meaning our light or signals could reach them in the future. In a non-accelerating universe, these two spheres would be similar in size, but in an accelerating universe, the affectable universe is much smaller than the observable universe and is getting smaller over time. We can see far more than we can touch. We are witnesses to a vast cosmos, but actors in only a tiny fraction of it. This asymmetry between seeing and reaching is one of the most profound features of our universe. It is a direct consequence of the accelerating expansion, which was itself a direct consequence of dark energy, which is itself a mystery we have not solved. We do not know why the universe is configured this way. We do not know if it had to be this way, or if there are other possible universes with different values of the cosmological constant where the expansion does not accelerate and the horizons do not close. The cosmological constant in our universe has a value of approximately 10 to the power of negative 122 inches natural units, which is extraordinarily small, but not zero. A value of 0 would mean no dark energy and no accelerating expansion. A larger value would mean faster acceleration and an even smaller accessible universe. We seem to live in a universe where the cosmological constant is just large enough to guarantee long-term cosmic isolation, but just small enough to allow a brief window, a few billion years, during which the evidence of the Big Bang and the large-scale structure of the cosmos is visible. We are living in that window right now. It will not last forever. The physicist Freeman Dyson, who spent decades thinking about the far future of the cosmos, described the ultimate fate of an isolated galaxy in terms that are both precise and melancholy. As the external galaxies vanish beyond the horizon, the merged Milky Way Andromeda galaxy will continue to evolve internally. Stars will burn out, one by one. New stars will form from the remaining gas, but eventually the gas will be exhausted. The last stars, the smallest red dwarfs with masses around 0.08 solar masses, will burn for perhaps 10 to 15 trillion years before fading to black. After that, the galaxy will be a collection of stellar remnants, white dwarfs, neutron stars, and black holes, slowly cooling, slowly decaying, slowly fading into the darkness of a universe that has forgotten its own past. What the expansion of space means for our question about the farthest galaxy is this. We are not asking about a difficult engineering challenge. We are asking about a physical impossibility. The farthest galaxy is beyond the cosmic event horizon. No speed achievable by any object with mass can close the gap. The gap is growing. And the acceleration of expansion ensures that it will continue growing, faster and faster, for the rest of cosmic time. The universe has drawn a line, and the farthest galaxy is on the other side of it. Not by a small margin, not by a distance that a slightly better technology could bridge, by a factor of 2. The galaxy is twice as far as the event horizon. It might as well be on the other side of infinity. And this is the core problem. Not just that the journey is long, or that the energy is enormous, or that the physics of acceleration is unforgiving. The core problem is that the cosmos itself is configured to prevent the journey. It is not that we are too slow, it is that the universe is too fast. Space is being manufactured between us and the galaxy at a rate that exceeds the speed of the fastest thing in existence. The road is being built behind us, extending the distance we have to cover, and the construction crews of dark energy never rest, never slow down, and never take a break. We are walking forward on a treadmill that is running backward, and the treadmill is speeding up. This realization did not come easily or quickly to the scientific community. For decades after Hubble's discovery of the expanding universe, cosmologists assumed that the expansion was slowing down under the gravitational pull of all the matter in the cosmos. The question was not whether the expansion would decelerate, but whether it would decelerate fast enough to halt and reverse, leading to a big crunch, or merely slow down and continue forever. Nobody expected acceleration. The discovery of accelerating expansion in 1998 was, in the words of one of its discoverers, like throwing a ball into the air and watching it fly upward, faster and faster, instead of coming back down. It violated every intuition about how gravity should work on cosmic scales, and it transformed our picture of the universe's future from a range of possibilities, some optimistic, some dramatic, into a single, quiet, inevitable conclusion: isolation, darkness, and cold. But here's what makes this truly terrifying. It is not the darkness, it is not the cold, it is the knowledge. We know what is coming. We can see the galaxies that will vanish. We can calculate the timeline. We can predict, with high precision, the moment when the last external galaxy crosses the event horizon and disappears from our sky forever. We have the mathematics to describe our own imprisonment. We understand the lock. We can see through the bars, and we know that no key exists. The ancient astronomers who looked up at the night sky saw a cosmos full of mystery but free of this particular despair. They did not know about the expansion. They did not know about dark energy. They believed the stars were fixed, the heavens eternal, and the universe a stable home for gods and mortals alike. We know better now, and the knowledge is heavy. The stars are not fixed. The heavens are not eternal. The universe is a brief experiment in complexity, a flickering pattern of matter and energy that will eventually smooth out into featureless equilibrium. And the farthest galaxy, that dim smudge in the infrared data from the James Webb Space Telescope, is a reminder of everything we will never reach. A postcard from the edge of the knowable, sent by a place that has already passed beyond the edge of the reachable. And there is one more dimension to this problem that deepens it further still. The universe is not just expanding in space, it is aging in time. The farthest galaxy is not just far away, it is in the past. The light we see from it was emitted 13.5 billion years ago. The galaxy, as it appears in our telescopes, no longer exists in that form. It has evolved. It has formed new stars, exhausted old ones, possibly merged with other galaxies, possibly been torn apart by gravitational encounters. The thing we see is a phantom, a recording, a snapshot from an era so remote that it predates the formation of our own sun by 9 billion years. We are looking at a place and a time simultaneously, and both are beyond our reach. This conflation of distance and time is one of the deepest features of cosmology. When we look at a galaxy 1 billion light-years away, we see it as it was 1 billion years ago. When we look at a galaxy 10 billion light-years away, we see it as it was 10 billion years ago. When we look at JADES GSZ140, we see it as it was 13.5 billion years ago, barely 300 million years after the Big Bang. We are looking back through time with every glance at the distant universe, and the farther we look, the deeper into the past we see, and the more the present reality of those galaxies diverges from the images we receive. This means that even if we could somehow reach the farthest galaxy, what we would find there would bear little resemblance to what we see from here. The tiny, luminous, star-forming galaxy captured by JWST has had 13.5 billion years to change. It may now be a massive elliptical galaxy, quiet and red, its star formation long exhausted. It may have been absorbed into a larger structure. It may have ejected its gas through galactic winds and become a dim, diffuse relic. We do not know. We cannot know. The light that would tell us what it looks like now will never reach us because the galaxy is beyond the event horizon. We have one picture, taken 13.5 billion years ago, and it is the only picture we will ever have. The album is closed, the camera is broken, the subject has left the room. This temporal dimension of the problem adds a layer of melancholy to the spatial one. We are separated from the farthest galaxy, not only by 33 billion light-years of expanding space, but also by 13.5 billion years of irrecoverable time. We cannot bridge the space. We cannot recover the time. We are stuck in our here and our now, looking outward and backward simultaneously, seeing the universe as it was but never as it is. The cosmos reveals its history to us like a book written in fading ink, with the earliest pages the most faded and the ending still unwritten. And we read what we can, knowing that the library is closing. Something is wrong with our assumptions about what the universe owes us. We assume it should be explorable. We assume that distance, given enough time and ingenuity, is always conquerable. We assume that seeing something means being able to reach it, but the universe makes no such promises. It shows us its beauty without guaranteeing us its company. It sends us light without inviting us to visit. It reveals its structure without offering us a map we can follow. The cosmos is generous with information but stingy with access. And the farthest galaxy, sitting in our data like a diamond locked in a vault, is the purest expression of this cosmic bargain. We can look, we cannot touch, we can know, we cannot go. But perhaps, amid the impossibilities of conventional travel, there are stranger possibilities. Perhaps the equations of general relativity contain doors we have not yet opened. Perhaps the quantum realm offers shortcuts we have not yet discovered. Perhaps there are ways to circumvent the speed of light that do not violate it, ways to move not through space but with space, not against the expansion but around it. Physicists have proposed several such ideas over the decades, each one brilliant, each one tantalizing, and each one, upon close examination, revealing its own set of problems that may be just as fundamental as the ones they claim to solve. The impossibility of reaching the farthest galaxy through conventional means has not stopped physicists from searching for alternatives. The history of physics is, in many ways, a history of finding loopholes. Newtonian mechanics seemed complete until Maxwell's equations revealed light as an electromagnetic wave and demanded a new framework. Classical physics seemed settled until quantum mechanics overturned its certainties at the smallest scales. And general relativity, the theory that governs the large-scale structure of the universe, has its own set of exotic solutions. Strange configurations of spacetime that are technically permitted by Einstein's field equations, and that suggest space and time can be manipulated in ways that seem to violate common sense. Over the decades, several serious proposals have emerged for faster-than-light travel, or its functional equivalent, each grounded in legitimate physics, each offering a tantalizing glimpse of possibility. And each, when examined closely, reveals limitations so severe that they amount to a different form of impossibility. Let us examine 5 of these proposals in detail, because each one illuminates a different aspect of the wall we are trying to climb. The first and most famous proposal is the Alcubierre warp drive. In 1994, a Mexican theoretical physicist named Miguel Alcubierre, then a graduate student at Cardiff University in Wales, published a remarkable paper in the journal Classical and Quantum Gravity. The paper was titled The Warp Drive, Hyperfast Travel Within General Relativity, and it demonstrated something that many physicists had assumed was impossible. Alcubierre showed that Einstein's equations permit a configuration of spacetime in which a bubble of flat, undistorted space is enclosed within a region where space is contracted in front of the bubble and expanded behind it. A spacecraft sitting inside this bubble would be perfectly at rest within its local frame of reference. It would experience no acceleration, no time dilation, and no relativistic effects. But the bubble itself, this distortion of the spacetime metric, would move forward at an arbitrary speed. And since the bubble is a feature of spacetime geometry rather than a material object moving through space, its motion is not subject to the speed of light limit. The spacecraft inside would be carried along like a surfer on a wave, the wave moving at superluminal speed while the surfer remains stationary relative to the water beneath. The mathematics is valid. Alcubierre's metric is a legitimate solution to Einstein's field equations. It does not violate general relativity. It exploits a feature of the theory that most people overlook. The speed of light limit applies to objects moving through spacetime, not to spacetime itself. Space can expand or contract at any rate. We already know this from the expansion of the universe, which carries galaxies apart faster than light at sufficient distances. Alcubierre simply proposed harnessing this property in a controlled, localized way. Instead of the entire universe expanding, you would expand the space behind a small bubble and contract the space ahead of it, creating a net forward motion that could, in principle, be faster than light. The paper made waves immediately. Here was a theoretical framework for faster-than-light travel that did not require abandoning Einstein's physics. It did not invoke new dimensions, exotic particles with imaginary mass, or the abandonment of known physical law. It worked entirely within general relativity. The possibilities seemed momentous. But here's the problem. The Alcubierre drive requires a form of matter with negative energy density, not negative charge, not negative mass, in the science fiction sense. Negative energy density, which means that the matter would need to have less energy than the vacuum of empty space. This is called exotic matter, and it violates what physicists call the energy conditions of general relativity, specifically the weak energy condition and the null energy condition. These conditions, while not proven as absolute laws of nature, are satisfied by every form of matter ever observed or created. Ordinary matter has positive energy. Antimatter has positive energy. Radiation has positive energy. Even the vacuum of empty space, according to quantum field theory, has positive or zero energy density depending on the model. Negative energy density is not just rare. It is, as far as we know, non-existent in any macroscopic sustained form. There are tiny exceptions. Quantum field theory predicts that under very specific conditions, such as the Casimir effect between two closely spaced conducting plates in a vacuum, the energy density can dip slightly below zero for extremely brief periods in extremely small volumes, but the Alcubierre drive does not need a tiny quantum fluctuation. It needs a massive, sustained, precisely shaped shell of negative energy surrounding the spacecraft. Early estimates by Alcubierre and others calculated that the total negative energy required would be approximately equal to the mass energy of the entire observable universe. Later refinements reduced this estimate significantly. In 1999, the Belgian physicist Chris van den Broek showed that by modifying the geometry of the bubble, the energy requirement could be reduced dramatically, perhaps to the mass energy of a few solar masses. More recently, Harold White at NASA's Eagle Works laboratory and Eric Lentz at the University of Göttingen have proposed further optimizations, suggesting that the energy might be reduced to the mass energy of a few hundred kilograms or even less. But even the most optimistic estimates require exotic matter, a substance we do not know how to create, in a configuration we do not know how to build, sustained by a mechanism we do not understand, and the problems compound. In 2012, 3 theoretical physicists, Stefano Finazzi, Stefano Liberati, and Carlos Barcelo, published an analysis of the quantum effects associated with an Alcubierre bubble. They found that the boundary of the bubble, the region where space transitions from contracted to expanded, would produce Hawking-like radiation directed inward. This radiation would flood the interior of the bubble with lethal energies, destroying anything inside. Additionally, as the bubble moves through the interstellar medium, it would accumulate particles on its forward boundary, sweeping up hydrogen atoms, cosmic dust, and photons from the cosmic microwave background. These particles would be trapped on the bubble wall, gaining energy as the bubble accelerates. When the bubble decelerates at the destination, all of this accumulated energy would be released in a catastrophic forward burst. The numbers are striking. A warp bubble arriving at a destination after traveling at 10 times the speed of light through a typical interstellar medium could release more energy than a supernova, concentrated in a narrow beam aimed directly at whatever is at the destination. The warp drive would not be a vehicle, it would be a weapon. It would not arrive at the farthest galaxy, it would sterilize it. There is also a less dramatic but equally fatal problem: control. The occupants of the bubble, sitting inside their pocket of flat spacetime, would have no causal connection to the bubble wall. They could not steer it, accelerate it, or stop it. Commands sent from inside the bubble to the wall would travel at the speed of light, but the wall is moving faster than light relative to the outside universe. The commands would never arrive. The warp drive, even if it could be built and powered and shielded, would be uncontrollable. It would be a train with no brakes, no steering wheel, and no way for the passengers to communicate with the driver, because there is no driver. The destination would have to be set before departure, with no possibility of course correction. So the Alcubierre warp drive remains a theoretical curiosity. It demonstrates that faster-than-light travel is not explicitly forbidden by general relativity, which is an important theoretical result. But it requires conditions so extreme, materials so speculative, and engineering so beyond our capabilities that it offers no practical path to the farthest galaxy. It is a door that is technically unlocked, but opens into a corridor filled with fire, radiation, and fundamental uncertainties that we do not know how to resolve. Before we leave the Alcubierre drive, there is one more detail worth considering. In 2021, the physicist Alexei Bobrik and Gianni Martir published a paper proposing a new class of warp drive solutions that they called general warp drives. Their framework showed that some warp configurations might be possible, with positive energy alone, eliminating the need for exotic matter. However, the positive energy warp drives they described were subluminal, meaning they could not exceed the speed of light. They would essentially be a very efficient engine, not a faster-than-light transport. The superluminal warp drives, the ones that could actually help with reaching the farthest galaxy, still required negative energy. The result was a frustrating tease. The physics allows warp drives without exotic matter, but only slow ones. The fast ones still need the impossible ingredient. It is as if the universe has placed its loopholes just slightly out of reach, close enough to see but not close enough to use. This pattern, solutions that almost work but fall short at the critical moment, repeats throughout the physics of faster-than-light travel. The Casimir effect provides negative energy, but in quantities too small and geometries too constrained to power a warp drive or prop open a wormhole. Quantum entanglement creates instant correlations between distant particles, but those correlations cannot be used to transmit information faster than light, a result known as the no communication theorem. Quantum tunneling allows particles to cross energy barriers instantaneously, but the effect does not translate to macroscopic objects or superluminal travel. Each of these phenomena hints at a crack in the speed of light barrier, but when you push on the crack, it holds firm. The barrier is not brittle. It is elastic, giving slightly under pressure but never breaking. The second major proposal involves wormholes, structures that have captivated both physicists and the public imagination for nearly a century. A wormhole, also known as an Einstein-Rosen bridge, is a hypothetical tunnel through spacetime that connects two distant points in the universe. The concept emerged in 1935 when Albert Einstein and the physicist Nathan Rosen noticed that the Schwarzschild solution to Einstein's field equations, which describes the spacetime geometry around a non-rotating black hole, could be extended to create a bridge between two separate regions of spacetime. The bridge was not designed for travel. Einstein and Rosen were exploring the mathematical structure of black holes, not proposing a transportation system. But the idea of a shortcut through spacetime captured the imagination of physicists and eventually of the broader public. The key question was whether a wormhole could be made traversable, meaning whether a person or a spacecraft could enter one end and emerge safely from the other. In 1988, the physicist Kip Thorne at the California Institute of Technology, inspired by a question from his friend Carl Sagan, who was writing the novel Contact, published a landmark paper with his students Michael Morris and Olvi Yurtsever. The paper, titled Wormholes, Time Machines, and the Weak Energy Condition, analyzed the conditions under which a wormhole could be held open long enough for a human to pass through. The answer, once again, was exotic matter. Without negative energy density threading the throat of the wormhole, the tunnel would collapse almost instantly, far faster than anything could traverse it. The gravitational forces near the throat would be extreme, potentially spaghettifying any object that approached. But with exotic matter, the throat could be propped open, the gravitational forces could be managed, and the wormhole could function as a bridge. The idea is beautiful. Imagine two mouths, each one a spherical region in space, connected by a short tunnel. One mouth orbits Earth, the other orbits a star in the farthest galaxy. You step through the first mouth and emerge from the second, having crossed 33 billion light-years in a few steps. The trip takes seconds. The expansion of the universe is irrelevant. You have not traveled through space, you have bypassed it. But here's the problem. Several problems, in fact. First, exotic matter again. The same material we cannot produce, cannot sustain, and cannot control is required in even larger quantities for a traversable wormhole than for an Alcubierre drive. The amount needed to keep a wormhole open depends on the diameter of the throat. For a human-sized wormhole, roughly 2 meters in diameter, the negative energy requirement is equivalent to the mass energy of Jupiter, focused into a thin shell around the throat. For a larger wormhole, the requirement is proportionally greater. Second, there is the placement problem. To use a wormhole to reach the farthest galaxy, you would need to have one end of the wormhole already positioned at the farthest galaxy. But getting it there requires the very capability the wormhole is supposed to provide. You cannot send one end of a wormhole to a destination faster than light unless you already have a faster-than-light transport mechanism. This is a chicken-and-egg paradox of the most fundamental kind. Some theorists have proposed that one end could be moved slowly, at sublight speed, while the other remains near Earth. But at sublight speed, transporting the far end to a galaxy 33 billion light-years away would take longer than the age of the universe, and the expansion of space would carry the destination farther away during the transit. The wormhole mouth would never arrive. Third, stability. General relativity allows wormholes as mathematical solutions, but it does not guarantee their stability against perturbations. A small fluctuation in the exotic matter, a stray photon entering the throat, an asymmetry in the geometry, any of these could cause the wormhole to collapse, pinch off, or develop a singularity. Stephen Hawking proposed the chronology protection conjecture, suggesting that the laws of physics actively prevent the formation of stable structures that could be used for faster-than-light travel or time travel. The universe, Hawking argued, might contain a built-in defense against paradoxes, a mechanism that destabilizes any configuration of spacetime that threatens causality. If Hawking was right, then wormholes are not just impractical, they are physically forbidden. Fourth, in 2019, the physicists Daniel Jafferis, Aaron Wall, and Ping Gao proposed a new kind of traversable wormhole that does not require exotic matter in the traditional sense. Their construction involves two entangled black holes connected by a quantum wormhole, a structure suggested by the ER equals EPR conjecture proposed by Juan Maldacena and Leonard Susskind. In their model, a specific kind of interaction between the two sides of the wormhole, mediated by quantum information, could hold the throat open long enough for a signal to pass through. This was a significant theoretical advance, but the wormhole in question is microscopic, operating at the Planck scale, and the signal that could pass through would be a quantum state, not a human body. Scaling this construction up to macroscopic size raises all the same problems of exotic matter and stability that plagued the original proposals. The quantum wormhole is a proof of concept, not a blueprint for a starship. So wormholes like warp drives remain firmly theoretical. They demonstrate that the mathematics of general relativity is rich enough to include shortcuts through spacetime. But translating that mathematical possibility into physical reality requires conditions so extreme that they may be permanently beyond the reach of any civilization, no matter how advanced. The third approach we must consider is less exotic but no less daunting. It is the concept of the generation ship, sometimes called a world ship or an interstellar arc. The premise is straightforward. If you cannot cross interstellar distances in a single human lifetime, then build a vessel large enough to sustain a population for many generations. The travelers who depart from Earth will not be the ones who arrive. Their descendants will complete the journey, born and raised aboard the ship, knowing no other home. The concept has been studied seriously by professional engineers and physicists. The British Interplanetary Society has been particularly active in this area. In the 1970s, the Society conducted Project Daedalus, a 5-year study of an unmanned interstellar probe powered by inertial confinement fusion, using pellets of deuterium and helium-3 ignited by electron beams. The probe was designed to reach Barnard's star, about 5.9 light-years away, in approximately 50 years, achieving a cruise speed of about 12% of the speed of light. In the 1980s, Project Longshot studied a mission to Alpha Centauri using similar fusion technology. And in more recent years, the Breakthrough Starshot initiative, funded by Russian-Israeli billionaire Yuri Milner and announced in 2016 with the backing of the late Stephen Hawking, has proposed using ground-based laser arrays to accelerate gram-scale probes to 20% of the speed of light, reaching Alpha Centauri in about 20 years. These projects demonstrate that interstellar travel to the nearest stars might be achievable, at least in unmanned form, within a few generations. But a generation ship aimed at the farthest galaxy faces problems that are not merely harder versions of the same challenges. They are categorically different. At 10% of the speed of light, a reasonably ambitious speed for a fusion-powered vessel, the co-moving distance to JADESGSZ 140, 33 billion light-years, would take 330 billion years to cross, ignoring expansion. With expansion included, the journey is not merely long, it is impossible. The galaxy is receding at more than twice the speed of light, so a ship traveling at 10% of c would fall behind from the first moment of the journey and continue falling behind forever. No generation ship, regardless of its size, its population, its fuel reserves, or the number of generations it supports, can reach a destination that is moving away faster than the ship can approach it. The generations would be born and would die, one after another, aboard a vessel that is perpetually losing ground. The journey would not merely fail. It would fail by an increasing margin with every passing century. Even for galaxies within the cosmic event horizon, the challenges are formidable beyond comprehension. Consider a galaxy at the far edge of the event horizon, roughly 16 billion light-years away in co-moving distance. At 10% of light speed, the journey would take at least 160 billion years, ignoring expansion effects, which would make it longer still. During that time, the generation ship would need to maintain hull integrity, life support, genetic diversity, social cohesion, and cultural continuity across millions of generations. The longest continuous human civilization on Earth, arguably the ancient Egyptian civilization, lasted about 3,000 years. A generation ship would need to sustain itself for more than 50 million times longer. The psychological, sociological, biological, and engineering challenges are staggering. How do you prevent the ship's population from fragmenting into factions? How do you maintain knowledge and purpose across millions of generations? How do you prevent genetic drift, inbreeding, or evolutionary divergence from the original human species? How do you keep the ship's machinery working for 160 billion years when the oldest human artifacts on Earth are less than 3 million years old? These are not engineering problems that will be solved by better technology. They are structural problems inherent to any finite system operating over cosmological timescales. Entropy, the tendency of ordered systems to become disordered, is relentless. Over 160 billion years, every machine will break, every seal will leak, every circuit will corrode. Every material will fatigue. The ship would need not just maintenance but continuous rebuilding, using resources gathered from the interstellar medium or from the ship's own recycled components. It is difficult to imagine any physical structure surviving for even a billion years, let alone hundreds of billions. The fourth approach takes us away from physical travel entirely and into the realm of information. It is the concept of mind uploading, also called substrate-independent consciousness. The idea is that if a human mind is essentially a pattern of information encoded in the structure and activity of neurons, then it might be possible to copy that pattern and run it on a different physical substrate. A digital mind, running on a sufficiently powerful computer, would not need food, air, water, or sleep. It would not age. It would not be subject to the biological frailties that make long-duration spaceflight so challenging. And critically, it could be transmitted as a signal, beamed across space at the speed of light, and received at a distant location where it could be instantiated in a new physical form. This approach eliminates many of the mass and energy constraints of traditional spaceflight. You do not need to accelerate a massive ship. You do not need life support. You do not need fuel for deceleration. You need only a powerful enough transmitter and a receiver at the destination. The entire mass of the payload is reduced to the mass energy of a beam of electromagnetic radiation carrying the encoded mind. But here's the problem, and it is the same problem we keep encountering. The farthest galaxy is beyond the cosmic event horizon. No signal sent from Earth today, at any frequency, at any power, using any encoding, will ever reach it. The expansion of space between here and there is faster than the speed of light. A mind uploaded to a laser beam aimed at JADESGS Z140 would travel forever and never arrive. The beam would redshift as it traveled, its frequency decreasing, its energy dissipating, its information content gradually degrading. At some point, the photons carrying the encoded mind would have been redshifted to such low energies that they would be indistinguishable from the cosmic microwave background. The mind would not experience this dissolution. It would simply cease to exist, its patterns scattered into the noise of an expanding universe that is too large and too fast for any signal to cross. There are also deep philosophical questions about whether mind uploading is possible in the first place. The human brain contains approximately 86 billion neurons. Each neuron has, on average, about 7,000 synaptic connections to other neurons, creating a network of roughly 600 trillion synapses. Each synapse is not a simple binary switch. It is a complex biochemical structure with multiple receptor types, neurotransmitter concentrations, structural plasticity, and timing-dependent properties. The total information content of the brain, measured at synaptic resolution, is estimated at roughly 2.5 petabytes, though this is likely a lower bound. At molecular resolution, it could be much higher. At quantum resolution, higher still. Whether consciousness can be captured and transferred at any of these resolutions remains an open question. We do not have a theory of consciousness that tells us what level of detail is required. We do not know if the relevant information is entirely structural or if dynamic, temporal patterns are also essential. We do not know if quantum effects play a role in cognition, as some theorists like Roger Penrose and Stuart Hameroff have proposed. And we do not know the most fundamental question of all, whether a copy of a brain's pattern, running on a different substrate, would be the same person, a different person, or no person at all. The concept of mind uploading rests on philosophical assumptions that have not been resolved and may not be resolvable. The fifth and final approach is the most speculative, and it pushes us to the boundary between physics and pure imagination. It is the concept of engineering spacetime itself, of manipulating the expansion of the universe on local or regional scales to create corridors or channels through which travel would be possible. Some theorists have called this metric engineering or spacetime engineering. The idea is that an advanced enough civilization might learn to manipulate the curvature of spacetime using enormous concentrations of energy, effectively creating artificial regions of contracted space, artificial wormholes, or artificial zones where the expansion rate is reduced to zero or even reversed. This concept presupposes a level of technological advancement so far beyond our current capabilities that it has no meaningful comparison in human experience. The physicist Nikolai Kardashev proposed his famous classification system in 1964, ranking civilizations by their energy usage. A Type 1 civilization harnesses all the energy available on its planet, roughly 10 to the power of 16 watts. Earth is currently about a Type 0.73 on this scale. A Type 2 civilization harnesses the entire energy output of its star, roughly 10 to the power of 26 watts, perhaps by building a Dyson sphere or swarm around it. A Type 3 civilization commands the energy of its entire galaxy, roughly 10 to the power of 36 watts. Manipulating the metric of spacetime across cosmological distances might require energy at the Type 4 or Type V level, classifications that Kardashev himself did not define because they exceed the energy content of the observable universe. The numbers are striking when you consider the energy budget. The total mass energy content of the observable universe is approximately 4 times 10 to the power of 69 joules. To alter the expansion rate of space across a region spanning billions of light years, you might need to control a significant fraction of this energy and direct it with precision that defies comprehension. You would need to reshape the vacuum energy of empty space, the very property that drives the cosmological constant. You would need to alter the dark energy density in a controlled region without destabilizing the rest of the universe. The engineering precision required would be like adjusting the orbit of every individual atom in every star in every galaxy in the affected region, simultaneously, without error. This is not difficult. This is, by any reasonable assessment, beyond the scope of physical possibility. It is the kind of technology that belongs not to the future of our species, but to the mythology of gods. And even if such technology were possible, the timescale for developing it presents its own challenge. Humanity has existed for 300,000 years. Civilization has existed for about 10,000 years. Science, in its modern form, has existed for about 400 years. The progression from Galileo's telescope to the James Webb Space Telescope took 413 years. If the pace of fundamental discovery continues at a similar rate, and there is no guarantee that it will, it might take thousands or millions of years to develop the theoretical framework for spacetime engineering, and then additional centuries or millennia to develop the engineering capabilities, and then additional time to build the infrastructure, by which point the cosmic event horizon will have contracted further, the pool of reachable galaxies will have shrunk, and the farthest galaxy will be even farther away than it is today. We are in a race against the expansion of the universe, and the universe has a head start of 13.8 billion years. There is one more consideration that belongs in this discussion, and it is the most humbling of all. Even if every one of these proposals could be realized, even if exotic matter could be manufactured, and warp bubbles stabilized, and wormholes opened, and minds uploaded, and spacetime engineered, there is a deeper issue that none of them address. The universe is not just large, it is old, and it is changing. The farthest galaxy we observe is not as it is now. It is as it was 13.5 billion years ago. By the time any traveler or signal could reach it, even in principle, that galaxy would have changed beyond recognition. Stars would have been born and died 1,000 times over. Planets would have formed, evolved, and been destroyed. Any civilization that existed there when the light was emitted would have risen, flourished, and fallen long before the traveler arrives. The galaxy the traveler set out to reach would not be the galaxy that greets them. It would be a different place entirely, separated from the motivating image by billions of years of cosmic evolution. The traveler would be chasing a memory, a photograph of a place that no longer exists as it was, a ghost of a galaxy that has aged past recognition while the traveler was in transit. This is perhaps the deepest irony of interstellar and intergalactic travel. The more distant the destination, the greater the gap between the image that motivates the journey and the reality that awaits at the end. You see a beautiful galaxy shining in the data, you set out toward it, you cross unimaginable distances over unimaginable spans of time, and when you arrive, if you arrive, you find something else. Something older, something changed, something that does not remember being the thing you came to see. The journey was inspired by a snapshot, but snapshots do not wait. The universe moves on, regardless of who is watching and who is traveling. Time does not pause for the ambitious. It flows for everyone, everywhere, at the same relentless pace, except aboard your relativistic ship, where it slows to a crawl, making the wait shorter for you and longer for everything else. Let us now consider a variant of the generation ship concept that is more grounded in near-term physics, and see how it fares against the challenge. The concept is the light sail, a spacecraft propelled not by onboard fuel but by the pressure of light. The idea dates back to at least 1924, when the Russian-Soviet astronautics pioneer Frederick Sander proposed using the radiation pressure of sunlight to push thin reflective sheets through space. The physics is simple. Photons carry momentum. When a photon strikes a reflective surface, it transfers twice its momentum to the surface, once on impact and once on reflection. If the surface is large enough and light enough, the cumulative push of billions of photons can accelerate it to significant speeds. The Breakthrough Starshot project, announced in 2016, proposes to use this principle on an ambitious scale. A ground-based array of lasers, with a combined power of approximately 100 gigawatts, would illuminate a sail just a few meters across, attached to a payload weighing roughly 1 gram. The intense laser beam would push the sail to approximately 20% of the speed of light within about 10 minutes of illumination. At this speed, the probe would reach Alpha Centauri in roughly 20 years. The probe is too small to carry a human or even a substantial instrument package, but it could carry miniature cameras and communication equipment, enough to take photographs and transmit them back to Earth. The concept is elegant and, in principle, achievable with technology that is within a few decades of our current capabilities. But scaling it up to a mission capable of reaching a distant galaxy reveals fundamental limitations. At 20% of the speed of light, the co-moving distance to JADESGSZ 140 would require 165 billion years to cross, ignoring expansion. With expansion, the journey is impossible because the galaxy is receding at more than twice the speed of light. The light sail approach, like every other propulsion method, cannot outrun the expansion of space. Even for destinations within the event horizon, the light sail faces severe challenges at high speeds. At 20% of the speed of light, collisions with interstellar dust particles become highly energetic. A dust grain weighing just a microgram would strike the sail with an energy equivalent to several grams of TNT. Over a journey of billions of light years, the cumulative damage from these impacts would be catastrophic. The sail would need to be armored, which adds mass, which requires more laser power, which increases cost and complexity beyond any reasonable projection. There is a deeper lesson here, one that applies to all 5 proposals we have examined. Each one addresses a specific obstacle, a specific constraint, a specific bottleneck in the chain of requirements for reaching a distant galaxy. The Alcubierre drive addresses the speed limit. Wormholes address the distance. Generation ships address the time. Mind uploading addresses the fragility of biological travelers. Spacetime engineering addresses the expansion itself. But none of them addresses all the obstacles simultaneously. And the obstacles are not independent, they are coupled. The speed limit creates the time problem. The time problem creates the energy problem. The energy problem creates the mass problem. The mass problem creates the speed problem. They form a closed loop of constraints, each one reinforcing the others, and no single breakthrough can break the loop entirely. This interconnection of obstacles is what makes the problem so intractable. It is not that we need one miracle, it is that we need 5 or 6 miracles, all at once, each one building on the others. We need exotic matter to build a warp drive. We need warp drives to deliver wormhole mouths. We need wormholes to bypass the expansion. We need to survive the transit, which requires overcoming radiation and time. And we need to understand consciousness well enough to upload minds, in case biological survival proves impossible. Each miracle depends on the others. None can stand alone, and the probability of achieving all of them is not the sum of their individual probabilities, it is the product. And the product of several very small numbers is a very, very small number indeed. The physicist Enrico Fermi once asked, during a lunch conversation at Los Alamos in 1950, a question that has haunted cosmology ever since. Where is everybody? If the universe is so vast and so old, and if intelligent life is not extraordinarily rare, then why have we not detected any evidence of other civilizations? The question is known as the Fermi paradox, and it has dozens of proposed solutions, ranging from the mundane to the existential. But in the context of our discussion, a particularly chilling answer suggests itself. Perhaps no civilization, no matter how advanced, has ever solved the interconnected problems of intergalactic travel. Perhaps the obstacles we have catalogued are not merely difficult, perhaps they are absolute. Perhaps every civilization that has ever existed has looked out at the distant galaxies and calculated, as we have, that the journey is impossible. Perhaps the great silence is not the silence of civilizations that have not contacted us. It is the silence of civilizations that cannot contact anyone, because the universe is too large, too fast, and too indifferent for any message to cross the gaps. This possibility carries a weight that is difficult to articulate. It suggests that cosmic isolation is not a temporary condition, not a phase that civilizations pass through on their way to galactic maturity, but a permanent feature of existence. Every civilization is an island. Every galaxy is a closed system. The bridges we imagine between the stars are fantasies born of a universe that seemed smaller and simpler than it turned out to be. The real universe is vast, expanding, accelerating, and structured in a way that keeps its contents separated by distances that no speed, no energy, no technology, and no ingenuity can overcome. There is a mathematical concept called a limit, where a function approaches a value it can never actually reach. The speed of light is such a limit for massive objects. The cosmic event horizon is such a limit for signals and travelers. And the farthest galaxy sits beyond that limit, on the far side of the asymptote, in a region of the mathematical curve that real objects can never access. It is there, in the equations. It is there, in the data. We can calculate its properties. We can estimate its mass, its luminosity, its chemical composition, but we can never touch it. It exists, for us, only as numbers on a page and photons on a detector. The farthest galaxy is the ultimate example of something that is real but unreachable, present in our knowledge but absent from our future, a mathematical truth that our physical selves will never verify firsthand. And perhaps that is the final lesson of this section, that the universe contains more than we can access, that reality is larger than experience, that the map is bigger than the territory we can explore. We are cartographers of a cosmos we can survey but never fully visit, sketching the outlines of continents we will never set foot on, charting the depths of oceans we will never sail. The farthest galaxy is the most distant mark on our map, the faintest notation at the edge of the page, and beyond it, beyond the edge of our map entirely, there may be more, much more. Infinite amounts more, but we will never know. The cartographer has limits, and the page has an edge. And beyond that edge, the unknown is not waiting to be discovered. It is retreating, faster and faster, into the unmappable dark. We should also note that even within these 5 major proposals, there are dozens of sub-proposals and variations that researchers have explored. Solar gravitational lensing, which would use the sun's gravity as a natural magnifying lens to focus signals from distant objects, was proposed by physicist von Eschleman in 1979 and further developed by Claudio Marcone. The focal point of the sun's gravitational lens begins at about 550 astronomical units from the sun, roughly 82 billion kilometers, and a spacecraft positioned there could potentially resolve surface features of exoplanets around nearby stars. But this is a passive observational technique. It does not help you travel to those planets, let alone to the farthest galaxy. It lets you see better. It does not let you go farther. Similarly, proposals for antimatter-powered spacecraft, which would annihilate matter and antimatter to produce pure energy, face the problem that producing antimatter in useful quantities is currently beyond our capabilities. CERN produces approximately 10 to 15 nanograms of antihydrogen per year. Powering a spacecraft to even a significant fraction of light speed would require kilograms or tons of antimatter, an increase in production by a factor of more than 1 trillion, and the storage problem is equally daunting. Antimatter annihilates on contact with ordinary matter, releasing enormous energy. Containing it requires magnetic or electric traps operating in a perfect vacuum, and any failure in containment would result in an explosion equivalent to a nuclear bomb. The theoretical efficiency of antimatter propulsion is unmatched by any other known energy source. But the practical challenges of producing, storing, and using it are so far beyond current technology that antimatter engines remain in the same category as warp drives and wormholes. Beautiful in theory, devastating in practice. The landscape of proposed solutions to the intergalactic travel problem is rich and varied, populated by brilliant ideas and brilliant people, but the landscape has a common feature. Every path leads to a wall. Every solution uncovers a new impossibility. Every door opens into a room with a locked door at the far end. The universe, it seems, has anticipated our cleverness and built its barriers accordingly, not to frustrate us, not to challenge us, simply because the laws of physics, the laws that allow stars to shine and atoms to bond and minds to think, are the same laws that impose a speed limit, an energy floor, and an expansion rate that, taken together, confine us to our corner of the cosmos as surely as gravity confines us to the surface of the Earth. The prison is not cruel. It is merely complete. There is a way to see the situation clearly, and it is not comfortable. The universe appears to be structured with a fundamental limit on connection, not just a practical limit, not just a technological limit, a structural limit woven into the very mathematics that govern spacetime. This is not an accident of our position in the cosmos. It is not a consequence of our particular era. It is a feature of reality that would apply to any observer, at any location, at any time in the history of the universe, since the onset of accelerated expansion approximately 5 billion years ago. The isolation is not ours alone. It belongs to everyone and everything that exists or will ever exist. Think about what the cosmic event horizon truly means. It is not a wall. There is no physical barrier sitting at the edge of the reachable universe. There is no membrane, no force field, no boundary you could touch if you traveled far enough. The event horizon is a consequence of geometry and motion. It is the surface beyond which the recession velocity of space exceeds the speed of light, making it impossible for any signal to cross from one side to the other. It is invisible. It is imperceptible. A traveler crossing it would notice nothing unusual. The local physics would be the same on both sides, but the implications are absolute. Once a galaxy crosses the event horizon, it is gone. Not in the future, not in some poetic sense. Gone in the most rigorous physical sense. No interaction of any kind between the galaxy and us will ever occur again in any frame of reference for the rest of eternity. And the horizon is closing in. As the expansion accelerates, driven by the relentless push of dark energy, the co-moving distance to the event horizon shrinks. Galaxies that are currently just inside the boundary are drifting toward it. Given enough time, they will cross it and join the ever-growing population of galaxies that are permanently beyond our reach. The number of galaxies we can communicate with, even in principle, is shrinking. The observable universe is not growing. It is contracting, not in its total volume of space, but in its functional reach. Every second that passes, the pool of galaxies that could theoretically receive a signal from Earth becomes a little smaller. This is not a hypothetical future concern. It is happening right now, has been happening for billions of years, and will continue happening for the remaining lifespan of the cosmos. Let that sink in. We are not living in a universe that is gradually becoming more accessible, more connected, more open to exploration. We are living in a universe that is gradually becoming more isolated, more disconnected, more closed. The lights are going out, one by one, across the cosmic stage. Each extinguished light represents a galaxy passing beyond the horizon, taking with it every star, every planet, every possible civilization it might contain. The show is still running, but the theater is emptying. The astrophysicists Lawrence Krauss and Robert Scherer explored the long-term consequences of this cosmic isolation in a 2007 paper that has become a classic in the field. They calculated what the universe would look like to an observer in the far future, approximately 100 billion years from now. Their conclusion was stark. By that time, every galaxy outside the local group, our gravitationally bound cluster of galaxies dominated by the Milky Way and Andromeda, will have crossed the cosmic event horizon. The Milky Way and Andromeda will have merged into a single large elliptical galaxy, and this merged galaxy, along with a handful of small satellite galaxies, will be the only visible structure in the entire sky. The rest of the universe, the trillions of galaxies that populate our current view, will have vanished. An astronomer living in that era would look out at the cosmos and see nothing but their own galaxy. There would be no other galaxies visible at any wavelength. The cosmic microwave background radiation, which today permeates all of space at a temperature of 2.725 Kelvin, would have been redshifted to wavelengths so enormous that it would be undetectable by any instrument. The temperature of the radiation would have dropped to a value indistinguishable from absolute zero. The evidence of the Big Bang, the foundational event that created the universe, would be erased. The evidence of the expansion itself would be gone, because there would be no distant galaxies whose recession could be measured. The future astronomer would see a single galaxy floating in an apparently infinite, static, empty void, and they would have no way of knowing that the universe was ever anything different. Let that sink in. The evidence of our cosmic history will be erased by the very process that created it. The expansion that revealed the universe to us will eventually hide it again. Future civilizations, if they exist, will construct theories based on what they can observe, and those theories will be wrong, not because the scientists are careless or incompetent, but because the data will be gone. The universe will have destroyed its own autobiography. It will have shredded the evidence of its own birth, its own youth, its own rich and complex middle age, and the civilizations of the far future will live in ignorance, not of their own making but of the cosmos's making, prisoners of a universe that has erased its own memory. This is not science fiction. This is the straightforward, well-established prediction of the lambda CDM model, the standard model of cosmology, which has been validated by data from the Planck satellite, the Wilkinson microwave anisotropy probe, the Sloan Digital Sky Survey, the Dark Energy Survey, and numerous other observational programs. The model describes a universe dominated by dark energy, with a cosmological constant that drives exponential expansion. Its predictions for the far future are not speculative. They are mathematical consequences of the measured parameters, as certain as the prediction that the Sun will exhaust its hydrogen fuel in about 5 billion years. The heat death of the universe looms behind all of this. It is the most widely accepted scenario for the ultimate fate of the cosmos. It does not involve a dramatic collapse, a fiery explosion, or a cataclysmic rending of spacetime. It is the opposite. It is a slow, quiet, irreversible fade into nothingness. Over trillions of years, the stars will burn out. The first to go will be the massive blue giants which consume their fuel in just a few million years. Then the yellow stars like our Sun, which last roughly 10 billion years. Then the orange and red dwarfs, the most numerous and most fuel-efficient stars, which can burn for 10 to 15 trillion years. After the last red dwarf gutters and dies, the only sources of energy in the universe will be the slow decay of matter itself and the gradual evaporation of black holes through Hawking radiation. White dwarfs will cool to black dwarfs over quadrillions of years. Neutron stars will solidify and grow cold. Black holes will dominate the far future, growing slowly as they absorb stray matter and radiation, then shrinking over inconceivable timescales as they radiate away their mass. The timescales involved are beyond human comprehension. A stellar mass black hole, about 10 times the mass of the Sun, will take approximately 10 to the power of 67 years to evaporate through Hawking radiation. A supermassive black hole at the center of a galaxy, with a mass of 1 billion solar masses, will take approximately 10 to the power of 100 years. That last number is a googol, a 1 followed by 100 zeros. The current age of the universe, 13.8 billion years, is a speck of dust on the timeline of black hole evaporation. And after the last black hole evaporates, in about 10 to the power of 106 years, the universe will contain nothing but a thin, diffuse soup of photons, neutrinos, electrons, and positrons, spread so thin that no two particles will ever interact again. The temperature will be a fraction of a degree above absolute zero and falling. Entropy will be at its maximum. Nothing will happen. Nothing can happen. The universe will not be dead. Exactly. It will be complete. It will have reached the state of maximum disorder, the state toward which all physical processes inevitably drive, and it will remain in that state forever. Against this cosmic backdrop, the question of reaching the farthest galaxy acquires a different color, a different weight, a different kind of urgency. It is not just a question about distances and speeds and energies. It is a question about what it means to exist in a universe that has a beginning and an end, a universe that creates complexity and then dissolves it, a universe that builds galaxies and stars and planets and minds and then, slowly, disassembles every one of them. What does it mean to be a conscious being in such a universe? What does it mean to see the farthest galaxy and know that it is beyond your reach? What does it mean to understand the equations that describe your own confinement and to find no errors in them? The astrophysicist Carl Sagan said that we are a way for the cosmos to know itself. If this is true, and there is a beautiful precision to the idea, then the cosmos has placed severe limits on its own self-knowledge. Most of the universe will never be observed. Most of it will never be reached. Most of it will never be understood by any conscious being, because the distances are too great, the timescales too long, and the expansion too fast. We are like a person standing in a vast dark room with a small flickering candle, able to see a tiny sphere of space around ourselves, but knowing that the room extends far beyond the reach of the flame, and the room is getting bigger, and the candle is getting dimmer, and eventually the flame will go out. Something is deeply wrong with our assumptions about the universe and our place in it. We grew up with narratives of exploration and expansion. We imagined humanity spreading across the galaxy, colonizing distant worlds, establishing contact with alien civilizations. We imagined that the cosmos was a frontier, open and waiting, and that all we needed was the courage and technology to claim it. These narratives are not just optimistic, they are wrong. Not wrong in detail. Wrong in structure. The universe is not a frontier, it is a bounded region of spacetime, and the boundaries are closing. The galaxies we can see are exhibits in a museum that is shutting its doors. The light that reaches us from the farthest galaxies is the last communication we will ever receive from them. The cosmos is not inviting us to explore. It is showing us a slideshow of its youth and then drawing the curtains. This realization is not new. Physicists and cosmologists have understood the implications of accelerating expansion since the late 1990s. But the emotional weight of it, the philosophical gravity, has not yet fully penetrated our culture. We still tell stories of galactic empires and interstellar civilizations. We still imagine that the future holds more space, more access, more connection. But the physics says otherwise. The future holds less space, less access, less connection. Every year, the fraction of the universe we can reach grows smaller. Every year, the darkness beyond the horizon grows larger, and no amount of wishing, hoping, imagining, or engineering can change this, because it is not a problem, it is a fact. A fact as hard and cold and permanent as the equations of general relativity that describe it. The speed of light, which we think of as the ultimate speed, the fastest anything can go, is not fast enough, not even close. In a static universe, a universe that is not expanding, light speed would be sufficient to eventually reach any point, given enough time. But we do not live in a static universe. We live in a universe where the destination is running away, and the road between here and there is stretching with every step. The speed of light is the fastest possible messenger, and it is still too slow to deliver its message to most of the addresses in the cosmos. The cosmic phone book has trillions of entries. Most of them are already disconnected, and the disconnections will continue until only our local group remains, a small island of gravitationally bound matter in an infinite sea of emptiness. The implications for the search for extraterrestrial intelligence are sobering. If advanced civilizations exist in distant galaxies, we will never know about them. Their most powerful signals cannot reach us across the cosmic event horizon, and our signals cannot reach them. The SETI project, the search for extraterrestrial intelligence, has focused primarily on detecting signals from within our own galaxy, and this is the right approach. because signals from other galaxies would need to have been transmitted billions of years ago before the expansion carried those galaxies beyond the horizon. Even within the Milky Way, the distances are daunting. A signal from the far side of the galaxy takes 100,000 years to reach us. A reply takes another 100,000 years. A conversation would span geological epochs. And between galaxies, conversation is impossible. The great silence, the eerie absence of detected alien civilizations, may not be a paradox at all. It may be the natural condition of a universe that is too large and too fast for its inhabitants to find each other. We may not be alone in the cosmos, but we may be alone in every way that matters, separated not by indifference or hostility or the limitations of technology, but by the geometry of spacetime itself. Each civilization, an island in an archipelago, too vast and too expanding for any bridge, any signal, any light to cross. The isolation is not a failure of effort. It is a feature of the universe, and it is permanent. This is the deeper truth about reaching the farthest galaxy. It is not merely that we cannot get there with current or foreseeable technology. It is not merely that the energy requirements are astronomical. It is not merely that the time required exceeds the lifespan of stars. The deeper truth is that the universe itself is structured to prevent it. The same laws of physics that allow galaxies to form, that allow stars to shine, that allow atoms to bond into molecules and molecules into life, those same laws create the speed limit, the energy floor, and the expansion rate that confine us to our corner of the cosmos. Our existence and our confinement have the same cause. The physics that makes us is the physics that traps us, and there is no way to keep one without the other. Let us follow this thought further, because it leads somewhere important. The cosmological constant, the value that determines the rate of accelerating expansion, is measured at approximately 10 to the power of negative 122 inches natural Planck units. This is one of the most puzzling numbers in all of physics. It is extraordinarily small, far smaller than the value predicted by straightforward quantum field theory calculations, which give a number roughly 10 to the power of 120 times larger. This discrepancy, known as the cosmological constant problem, has been called the worst prediction in the history of physics. Nobody knows why the cosmological constant is so small. Nobody knows why it is not zero either. It sits at a value that is just barely large enough to drive the expansion of the universe, but just barely small enough to have allowed galaxies, stars, and planets to form in the first place. If the cosmological constant were much larger, the expansion would have been so rapid that matter could never have clumped together under gravity. No galaxies would have formed, no stars, no planets, no observers. If it were exactly zero, there would be no accelerating expansion, no event horizon closing in, and no cosmic isolation. Galaxies would remain accessible, in principle, forever. We seem to live in a universe where the cosmological constant is balanced at a value that permits our existence but guarantees our confinement. It allows us to form but prevents us from spreading. It creates observers who can see the cosmos but cannot explore it. Whether this is a coincidence, a necessity, or a selection effect of some kind is one of the deepest questions in modern physics. Some physicists, notably Steven Weinberg, Leonard Susskind, and others associated with the string theory landscape, have proposed that the cosmological constant is not a fundamental constant at all, but a local property that varies from one region of a vast multiverse to another. In this picture, our universe is one pocket in an infinite sea of pocket universes, each with its own value of the cosmological constant. We observe a small non-zero value, not because the laws of physics demand it, but because only in regions where the value is in the right range can observers exist to measure it. This is the anthropic argument. It is elegant and frustrating in equal measure. It explains the value without truly explaining it. It tells us that the cosmological constant is what it is because we are here to measure it, but it does not tell us why the multiverse exists, or whether it is the right framework for thinking about these questions. Regardless of the explanation, the consequence is the same. The cosmological constant is what it is, and its effect on the expansion of the universe is what it is, and the result is a cosmos where the reachable fraction shrinks over time and the farthest galaxies are permanently beyond our grasp. This is not a matter of opinion or interpretation. It is a measured quantity with measured consequences, and those consequences include the permanent isolation of distant galaxies. There is another dimension to the deeper truth that deserves attention. We have focused primarily on the spatial isolation imposed by the expansion of the universe, but there is also temporal isolation, and it is equally profound. The farthest galaxy, JADESGSZ140, exists in our data as an image from 13.5 billion years ago. The galaxy as it is now, at this very moment, is unknown to us and will remain unknown forever. No light from its current state will ever reach us. We have one portrait, painted in ancient photons, and that portrait is all we will ever have. But the temporal isolation goes further than this. Consider our own far future. In trillions of years, after the last stars have died and the last black holes have evaporated, the universe will enter a state of maximum entropy. All energy gradients will have been smoothed out. All structure will have dissolved. All information will have been randomized. In this state, it is not just that no one will be able to reach the farthest galaxy. It is that there will be no one left to care. Consciousness, as far as we understand it, requires energy gradients. It requires the flow of information, which requires differences in temperature, pressure, chemical concentration, or electrical potential. In a universe at thermal equilibrium, there are no gradients. There is no flow, there is no information processing, there is no thought. The universe will not merely be lifeless, it will be thoughtless. It will be a cosmos without observers, without questions, without wonder. This is the temporal horizon that mirrors the spatial one. We are bounded not just by the edge of the reachable universe, but by the edge of the livable universe. And both edges are approaching. The spatial edge approaches as the cosmic event horizon contracts. The temporal edge approaches as the stars burn out and the energy sources dwindle. We live in a window, a brief interval of cosmic history during which the conditions for observation, thought, and existence are met. That window opened roughly 13.8 billion years ago and will close slowly and irrevocably over the next tens of trillions of years. We are in the middle of it. The view is spectacular, but the window is finite, and it is closing. The physicist Roger Penrose has suggested that the far future of the universe might, through a conformal transformation of spacetime, resemble the conditions at the Big Bang, giving rise to a new cycle of cosmic expansion and complexity. He calls this idea conformal, cyclic cosmology. Others have proposed that quantum fluctuations in the vacuum might spontaneously create new Big Bangs, new pocket universes, new beginnings out of the heat death of the old cosmos. These ideas are speculative, and they are not currently supported by observational evidence. But they speak to a deep human need to find hope beyond the horizons, to imagine that the story does not end in silence and cold and darkness. Whether this hope is justified by physics or merely comforting, it does not change the situation for us, here, now. We live in this universe, in this epoch, with this cosmological constant, and the farthest galaxy is beyond our reach. The French mathematician and philosopher Blaise Pascal wrote, in his Pensées, about the silence of the infinite spaces that terrified him. He was writing in the 17th century, long before Hubble and Einstein and dark energy, but his intuition was sound. The universe is silent. Not because it contains nothing, but because it contains everything separated by distances that swallow every voice, every signal, every cry into the vastness. The farthest galaxy emitted its light more than 13 billion years ago, and that light is the closest thing to a message we will ever receive from it. It is not a message with content, not a signal with information, not a greeting from a distant civilization. It is simply the afterglow of existence, photons that happen to have traveled in our direction, carrying the faint signature of a galaxy that was young when the universe was young. It arrived by chance. It carried no intention, and yet we detected it, measured it, analyzed it, and understood what it meant, and that understanding, fragile and incomplete as it is the only bridge we will ever build to the farthest galaxy. Not a bridge of matter or energy, a bridge of comprehension. There is a kind of reaching that does not require physical travel. There is a kind of contact that does not require signals. When we look at the light of the farthest galaxy and understand what it is, where it came from, how old it is, and what it tells us about the conditions in the early universe, we are making contact with a distant place in the only way the universe permits. We are understanding it. We are holding its image in our minds, processing its data in our computers, fitting its properties into our models of cosmic evolution. We are reaching it with our thoughts, if not with our hands. And this kind of reaching, while it does not satisfy the explorer's desire to stand on distant shores, is not nothing. It is, in fact, the most extraordinary thing that a collection of atoms on a small rocky planet in an ordinary galaxy has ever accomplished. We are made of the same matter that fills the farthest galaxy. We are governed by the same physics, and through the accident of consciousness, we have become able to understand the cosmos that made us, even the parts of it we can never visit. This is not science fiction. This is the actual situation. We are conscious beings in an expanding universe, temporary patterns of complexity in a sea of entropy, aware of our own impermanence and the impermanence of everything around us. We know that the farthest galaxy is unreachable. We know that the observable universe is contracting. We know that the stars will eventually die and the black holes will eventually evaporate and the last traces of structure will eventually dissolve into the featureless equilibrium of heat death. We know all of this, and yet we continue to look up, to build telescopes, to ask questions, to seek understanding. That persistence, that refusal to stop wondering even in the face of ultimate futility, may be the most remarkable thing about us. It is certainly the most human. And there is one more thread to follow, one that ties together everything we have discussed and points toward the emotional core of this entire question. The farthest galaxy exists in two states simultaneously. It exists as data, as photons captured by the James Webb Space Telescope, as a spectrum analyzed by astronomers, as a redshift value and a co-moving distance, and a set of physical parameters recorded in scientific journals. In this form, it is knowable, measurable, real. But it also exists as a physical object, a collection of stars and gas and dust and dark matter, sitting at a location in space-time that we cannot access. In this form, it is real but unknowable in its present state. We have the portrait but not the person. We have the echo but not the voice. This duality, this split between the knowable image and the unknowable reality, is a metaphor for our relationship with the universe as a whole. We see the cosmos in the light of the past. Every observation we make is an observation of something that has already changed. The sun we see is the sun as it was 8 minutes ago. The nearest star is as it was 4 years ago. The nearest galaxy as it was 2.5 million years ago, and the farthest galaxy as it was more than 13 billion years ago. We live in a perpetual present, surrounded by images of the past, unable to see the present state of anything beyond our own planet. The universe gives us its history but withholds its present. It shares its memories but keeps its secrets. This is, in a sense, the human condition projected onto the cosmic scale. We are always looking backward. We are always seeing what was, never what is. And the farther we look, the deeper into the past we see, the wider the gap between image and reality becomes. The farthest galaxy is the extreme case, the limiting example, the place where the gap between what we see and what exists has become so large that the two things might as well be different objects entirely. We see a young, bright, star-forming galaxy from the dawn of time. The galaxy that exists now, 33 billion light-years away and 13.5 billion years older, is something we cannot imagine with confidence. We have models, yes. We have predictions, but we have no observations. The curtain is down, the show is over, at least for us. And yet the photons arrived, against all odds, across all that distance, through all that expanding space, they arrived. They carried their message faithfully for 13 billion years. They did not know they were carrying a message. They are not conscious. They are not aware. They are simply quanta of electromagnetic radiation, following the geodesics of spacetime according to the equations of Maxwell and Einstein. But they arrived, and we were here to receive them, and because we were here, the message was heard. Not understood in the way a letter is understood, but understood in the way that physics is understood. The wavelength was measured, the redshift was calculated, the distance was derived, the age was estimated, and in that chain of measurements, the farthest galaxy became part of our story. It entered our awareness, it joined the inventory of known things, and that is a form of contact, however one-sided. That is a form of reaching, however incomplete. What does it mean for us, here, now, on this small rocky world? We have followed a question to its conclusion. The farthest galaxy is unreachable. Most of the universe is unreachable. The observable cosmos, this sphere of ancient light that we survey with our telescopes, is a shrinking island in an ocean of expanding space. And we are on that island, looking out at the tide, knowing it will never recede. There is a temptation to feel despair at this realization, to see the expanding universe as a prison, its horizons closing in like the walls of a contracting cell. And perhaps there is something valid in that feeling. Humans are, by nature, explorers. Our ancestors crossed oceans on wooden ships. They climbed the highest mountains. They walked on the surface of the moon, 384,000 kilometers from home, and planted a flag in the dust. The idea that there are places we can never go, no matter how clever or determined we become, no matter how many centuries of technological progress we accumulate, runs against something deep in our self-image as a species. We are not accustomed to permanent limits. We break through them. That is what we do. That is what we have always done. But the universe is not a problem designed for us to solve. It is not a challenge issued with the expectation that it will be met. It is a physical reality governed by mathematical laws, and those laws do not care about our ambitions. The expansion of space is not a test. It is a process. Dark energy is not an adversary. It is a property of the vacuum. The cosmic event horizon is not a barrier placed in our path to see if we are clever enough to overcome it. It is a consequence of geometry. These things simply are. They were not created to frustrate us. They were not created at all, in any purposeful sense. They are features of a universe that follows principles we have learned to describe, but not to alter. And perhaps there is something liberating in that understanding. If the universe is not a challenge, then our failure to overcome it is not a failure at all. It is simply a recognition of reality, a recognition that is itself a triumph, because recognizing reality accurately and without flinching is one of the hardest things a conscious mind can do. It is much easier to tell stories, to imagine that the future will bring warp drives and wormholes and galactic civilizations spanning billions of light years. Those stories are comforting, they are exciting, and they are almost certainly wrong. The future, if the physics is correct, brings increasing isolation, decreasing complexity, and the slow fading of every light in the sky except the stars in our own merged galaxy. That is not a story we want to hear, but it may be the story that is true, and there is a dignity in accepting a true story, even an unwelcome one. The knowledge that we cannot reach the farthest galaxy does not diminish us, it locates us. It tells us where we are and what we are. A brief, complex arrangement of matter and energy on a pale blue dot, aware of its own impermanence, capable of wonder in the face of incomprehensible scale. That capacity for wonder is not diminished by the impossibility of the journey. If anything, it is deepened by it. To see the farthest galaxy and know that it is beyond reach, and to find that knowledge beautiful rather than crushing, is perhaps the highest expression of what it means to be a conscious being in this particular universe. There is a philosophical tradition that finds meaning not in the achievement of goals, but in the quality of awareness itself. The Stoics of ancient Greece and Rome spoke of living according to nature, accepting what cannot be changed, and finding freedom in the discipline of understanding. The universe, in its vast and quiet indifference, offers a similar lesson. We cannot cross the cosmic void. We cannot outlast the stars. We cannot reach the farthest galaxies or send messages to whatever civilizations might inhabit them. but we can understand why. We can trace the equations that govern the expansion. We can measure the redshift of distant light with precision. We can build telescopes that see 13.5 billion years into the past. And in doing so, we participate in the universe's self-knowledge in the only way available to us, not by reaching everything, but by comprehending as much as we can from where we stand. There is beauty in a horizon. Every horizon, by definition, is a place you cannot reach. The horizon on Earth retreats as you approach it, always the same distance away, always marking the boundary of your sight but never your actual limit. You can always walk toward it and find new ground beneath your feet. The cosmic event horizon is different. It is a true limit, not an optical illusion. It marks not just the edge of what you can see, but the edge of what you can ever affect or be affected by. And yet, even this ultimate horizon carries a kind of beauty. It defines the edge of our cosmic neighborhood, the boundary of the playground within which all of our stories unfold. Every love affair, every war, every symphony, every extinction event, every birth and death of every star within the observable universe happens inside this bounded region of spacetime. It is our home, in the deepest possible sense, not our planet, not our solar system, not our galaxy, our horizon. Everything within it is connected to us by the web of light and gravity. Everything beyond it is a part, has always been a part, and will always be a part. The farthest galaxy we have confirmed is JADES GSZ 140. Its light is a message from the earliest epoch of cosmic history, a time when the first stars were igniting and the first heavy elements were being forged in nuclear furnaces deep inside those stars. Carbon, oxygen, nitrogen, the building blocks of biology, were being created for the first time in the universe's history. That message has traveled 13.5 billion years to reach us. It has crossed a universe that has changed almost beyond recognition during the journey. It has been stretched and weakened and shifted from ultraviolet to infrared, and it has arrived. Against all the odds imposed by distance and expansion and time, it has arrived, not as a signal from the galaxy as it is now, but as a record of the galaxy as it was. A portrait from the dawn of time, painted in photons that survived the longest journey any light has ever made to reach a human instrument. That is not nothing. That is extraordinary. The fact that we can see back to within 300 million years of the Big Bang, from our vantage point on a small planet orbiting a middle-aged star in the suburbs of an ordinary spiral galaxy, is one of the most remarkable achievements of our species. It is an achievement not of engineering, though engineering enabled it. It is an achievement of understanding, of mathematics, of patience, of the slow, cumulative, collaborative effort of thousands of scientists across centuries, each one building on the work of those who came before, each one pushing the boundary of knowledge a little farther into the dark. We cannot touch the farthest galaxy. We cannot visit it. We cannot send it a message or receive a reply, but we can see it. We can study it. We can understand what it was and, through our cosmological models, estimate what it might have become, and in doing so, we honor the photons that crossed the void to reach us. Those ancient messengers, those patient travelers, carry the last knowable information about a place we will never know firsthand. They are the only ambassadors we will ever receive from the farthest reaches of the observable universe, and we received them. We decoded their message, we understood their origin, and we recorded what they told us, adding one more entry to the growing ledger of human knowledge. Perhaps the most important implication of all is this: time matters. Not just in the sense that time is passing and we should make the most of it, though that is true, but in the deeper sense that the cosmic window through which we observe the universe is not permanent. The evidence that allows us to understand the Big Bang, the expansion, and the large-scale structure of the cosmos is available now, but it will not be available forever. Future civilizations, born in the era of isolation, will not have this evidence. They will live in a universe that has erased its own history. They will look out and see a single galaxy in an infinite void, and they will not know what they are missing. We are the ones who can see. We are the ones who live in the epoch of cosmic transparency, when the evidence is still visible, when the distant galaxies are still glowing, when the cosmic microwave background is still detectable. We are the custodians of cosmic knowledge, the only generation, in the broadest sense, that will ever have access to the full story. And perhaps our responsibility is not to reach the farthest galaxy, but to understand it, to record it, to preserve the knowledge of what the universe truly is before the evidence fades and the curtain falls. Perhaps our role in the cosmos is not explorer but witness. Not the one who goes everywhere, but the one who sees everything that can be seen and writes it down, so that, in some form, the knowledge endures even after the light is gone. There is a pause that comes naturally here, a moment where the mind steps back from the numbers and the equations and the relentless logic of physics, and simply sits with the weight of what has been said. The universe is not waiting for us, it is leaving us. It has been leaving us since the expansion began to accelerate, and it will continue leaving us for the rest of eternity. This is the context of our existence. This is the stage on which every human drama plays out. Not an infinite frontier, but a finite island. Not an open road, but a closing circle. And within that circle, everything we know and love and value exists. Perhaps that is what makes it precious. Things that last forever are hard to value. They will always be there. There is no urgency, no weight, no poignancy. But things that are finite, things that are bounded, things that will one day end, these carry a gravity that the infinite cannot match. The observable universe is finite. Our time within it is finite. The window of cosmic transparency is finite, and the light from the farthest galaxy is finite, a fixed number of photons that travelled a fixed distance over a fixed time and arrived at a fixed moment in history. That finitude is not a deficiency. It is what makes the light meaningful. It is what makes the observation extraordinary. It is what makes our existence, brief and bounded as it is, worth something in the cold accounting of the cosmos. We are temporary patterns in matter and energy, briefly complex enough to understand our own impermanence. That understanding is the rarest thing in the universe, more rare than gold or platinum, more rare than diamonds or neutron star material. Because understanding requires consciousness, and consciousness requires complexity, and complexity requires energy gradients, and energy gradients are being smoothed out by the relentless second law of thermodynamics. Every moment of awareness we experience is a small victory against entropy. Every question we ask is an act of defiance against a universe that tends towards sameness and stillness and silence. And the biggest question of all, whether we can reach the farthest galaxy, turns out to have a quiet, final answer. No, we cannot, but we can understand why. And that understanding is itself a kind of journey, not across space, not through time, but through the landscape of knowledge, from ignorance to clarity, from assumption to truth. It is the only journey the universe offers us without reservation, and it is enough. It has to be enough, because it is all we have. There is a galaxy at the edge of everything we can see. It is 33 billion light-years away. Its light left it more than 13 billion years ago, when the universe was young and hot and dense, when the first stars were just beginning to burn, when the cosmos was a fraction of its current size and a fraction of its current age. That light has been travelling ever since, crossing the expanding void, losing energy with every billion years of transit, stretching from ultraviolet into infrared, dimming from a beacon into a whisper. It arrived at a mirror in space, a gold-coated telescope orbiting the Sun at the second Lagrange point, 1.5 million kilometers from Earth, and it told us something. It told us that the universe was already building galaxies when it was barely 300 million years old. It told us that the raw materials of cosmic structure, hydrogen, helium, and the first traces of heavier elements were already assembling into organized forms. It told us that light can carry a memory across almost the entire age of the cosmos, that photons are patient, that the universe keeps records even as it expands. And it told us quietly, with the gentleness that only a photon travelling for 13 billion years can possess, that the source of that light is gone from our reach, not destroyed, not extinguished, not dead, just gone, carried away by the expansion of the space between us, accelerating into a region of the universe that we will never access, never visit, never signal, never touch. The galaxy exists. It is out there right now, 33 billion light-years away, doing whatever galaxies do after 13 billion years of evolution. But it is as inaccessible to us as a memory of a person who has moved to the far side of the world and cannot be contacted. We have the photograph. We do not have the person. The question we asked at the beginning was simple. How long would it really take to reach the farthest galaxy? And the answer, as we have traced it through the physics of expansion and the mathematics of relativistic motion and the engineering of propulsion and the nature of spacetime itself, is not a number. It is a negation. It cannot be done. It would take forever, and even forever would not be enough. The galaxy is moving away faster than anything can chase it. The space between us and it is growing, faster than light can cross it. The energy required to approach light speed is equivalent to the output of stars. The time required, even with time dilation, exceeds the lifespan of the universe itself. And the cosmos is arranged in such a way that the problem gets worse with every passing moment. The cosmic event horizon is closing in. The galaxies beyond it are slipping away. The reachable universe is shrinking. This is the reality of our cosmic position. We are embedded in a universe of extraordinary size and beauty, surrounded by hundreds of billions of galaxies within the observable sphere, each containing hundreds of billions of stars, each star potentially orbited by worlds we will never see. The scale is magnificent. The isolation is absolute. We can look, but we cannot go. We can receive ancient light, but we cannot send replies that will ever arrive. We are witnesses to a cosmos that reveals itself in photons and then retreats behind the advancing curtain of expansion, taking its secrets with it, leaving us with images and equations and a deep, quiet awareness of our own confinement. And yet, there is something in the human mind that refuses to let this be a tragedy. Perhaps it is not one. Perhaps the universe is not diminished by being unreachable. Perhaps we are not diminished by being confined. The light of the farthest galaxy did reach us. It made the journey. It survived 13 billion years of expansion, 13 billion years of redshifting, 13 billion years of empty space and cosmic evolution, and the slow stretching of its wavelengths from the energetic blue of ultraviolet to the long, slow pulse of infrared. And it landed on a mirror that human beings designed, built, and placed in orbit around the Sunday that is connection. Faint, one-directional, ancient, and finite, but connection nonetheless. We are linked to the farthest galaxy by a thread of light so thin and so old that it barely exists, but it exists. And because it exists, so does our understanding, so does our awareness, so does our ability to ask the question in the first place. The universe is not silent, it is whispering. It has been whispering for 13 billion years, in wavelengths we are only now learning to hear. Every photon that arrives from the distant past is a syllable in a story that the cosmos is telling about itself. It is a long story, a slow story. A story told not in words but in wavelengths, not in sentences but in spectra, not in chapters but in redshifts that encode the history of expansion. We are learning to read this story. We are getting better at it. Every new telescope, every new detector, every new algorithm that processes the data brings us closer to a complete reading of the cosmic text. And even though we know that the text is finite, that the last pages are being written as the distant galaxies fade beyond the horizon, we continue to read, because the reading itself is the point. The understanding itself is the destination. The journey we take is not across space, it is across the landscape of knowledge. And that journey has no event horizon, it has no speed limit. It has no expansion to outrun. It is bounded only by the limits of our curiosity, which, as far as we know, has none. We may never reach the farthest galaxy. We may never send a probe to its shores or stand on one of its planets and look back at the Milky Way from 33 billion light-years away. But we know it is there. We know it existed. We know what it looked like when the universe was young. We know its redshift, its luminosity, its approximate mass, its distance, and its age. And that knowledge, fragile and incomplete as it is the most extraordinary thing that a collection of atoms on a small rocky world has ever accomplished. We are stardust that learn to measure the stars. We are matter that learn to contemplate matter. We are the universe looking at itself from the inside, trying to understand its own geometry, its own history, its own limits. The farthest galaxy is unreachable. The universe is structured to ensure this. The expansion of space, driven by dark energy, enforced by the cosmological constant, described by the Friedmann equations, and confirmed by every observation we have made, guarantees that the vast majority of the cosmos will remain forever beyond our grasp. We are here, on our small planet, orbiting our average star, in the suburbs of our ordinary galaxy, inside the thin, shrinking shell of the reachable universe, and we are looking up, knowing, understanding, measuring, recording, accepting the distance and finding, in that acceptance, something that feels like peace. Not the peace of resignation, the peace of comprehension, the peace that comes from seeing things as they are, clearly and without illusion, and finding that the truth, even when it is vast and cold and final, carries its own kind of beauty. The cosmos gave us eyes to see it. It gave us minds to measure it. It gave us just enough light to know that it stretches farther than we can ever go. Perhaps that is enough. Perhaps the seeing is the reaching. Perhaps the understanding is the arrival. Perhaps the only journey that truly matters is the one that happens in the mind of the observer, tracing the path of an ancient photon backward through time and space, all the way to the beginning, all the way to the edge of everything. The farthest galaxy is 33 billion light-years away. Its light has been traveling since before the Earth existed. It arrived tonight on the mirror of a telescope, and it carried a single, simple, ancient message. You are not alone in the universe, but you are very, very far from everything else, and the distance is growing, and it will keep growing long after the last human eye has closed, long after the last telescope has powered down, long after the last star in the last galaxy has burned through its final reserves of hydrogen and dimmed to nothing. The expansion will continue. The void will deepen. The silence will thicken. And somewhere out there, 33 billion light-years away and receding, the farthest galaxy will continue to exist, alone in its own pocket of the cosmos, surrounded by its own event horizon, carrying its own stars and its own history, and perhaps its own observers who look out at their own shrinking sky and wonder, as we do, whether anyone else is out there. Perhaps they too have seen our galaxy in their own ancient light. Perhaps they too have calculated the distance and found it impossible. Perhaps they too have felt the quiet weight of cosmic solitude and found, within it, something that resembles understanding. We will never know, but the light arrived, and that was enough.